Circuit. This week we're in Vienna. There's a series of 6 local conferences. We already had one in Waterloo and in Nottingham. Now we're here at the Institute of Quantum Optics and Quantum Information in Vienna. The local organizer is Anne-Catherine de la Hamette. So give her the mic to give the initial introductions. Thank you.
Thank you. Welcome everyone. First, I want to thank Rick for organizing this great 6-week-long conference of the RQI Circuit in the different locations. Vienna is very happy to be part of this talk series. Then I also want to thank our speakers of today. You can already see the schedule in the background. We're going to hear about all the different kinds of research that is being done here in Vienna, both at IQOQI Vienna as well as University of Vienna. Then I want to thank the audience here for coming to the talks and listening to your fellow researchers. Yes, so let's then get started immediately. You see that today's afternoon is divided into 2 parts. We're first going to hear about 5 different talks and end with a presentation of IQOQI Vienna. We're then going to go into a nice coffee break, and then we're going to have a slightly longer second part of the afternoon, which you can see here. Good. So in order not to lose any time, I would like to introduce our first speaker, which is Časlav Brukner, who's going to tell us about quantum reference frames, indefinite causal order, Wigner, and his friends. I'm going to pass you the microphone.
Now starts.
Oh, that's okay. This was to be expected.
No, I think this will not work.
That's okay.
It's doing something.
Could you quickly send it to me?
But now it's totally blocked. Huh?
No.
Okay, give me the. Okay. Good morning, good afternoon, good evening, wherever you are. Thank you for coming, both for those who are here and those that follow us online. And I would like to start by thanking Anne-Catherine and Nick for organizing this event. I'm going to present some recent results from my own group. We work at the interplay between quantum theory and physics of space-time and try to employ operational quantum information tools to get insights in this interplay. I will tell you something about quantum reference frames in indefinite causal order, and I leave out Wigner and his friends for today. So let me go to the outline of the talk. I will first introduce, on the basis of simple examples, what I mean with classical coordinates. Then I will extend this notion to quantum coordinates and show 2 applications of the quantum coordinates, namely in description of superposition of semi-classical spacetimes and indefinite causal order, and at the end I will conclude. So half an hour is not long, so let me start immediately. Imagine that you have just 2 objects in the world. There is this kind of Earth, a larger object, and a small object, like an atom, and there is nothing else. And assume that there is a translational invariance, that all interactions depends only on the relative distance between these 2 objects. Now, usually, if we want to solve some problem, concrete problem, we introduce a coordinate system. And by introducing a coordinate system, we immediately introduce something which we call gauge degrees of freedom. So degrees of freedom that are not really physical, because they are just 2 objects, only the relative distance between them matters, But then we can think that there is some kind of hypothetical imaginary observer at the origin of this coordinate system that could measure the distance from this origin to the position of the two objects. But still, we should bear in our mind that all what is relevant in the end will be the relative degrees of freedom. Now, because the coordinate system and the choice of the coordinate system is irrelevant, sometimes we pick up exactly those that simplify the problem. For example, maybe the most simple situation here if we center the origin of the coordinate system at the center of Earth. Now, the reason why we can choose arbitrary coordinate systems is that we have this big idea of the theoretical physics that the physical laws preserve their form or are invariant under the choice of the coordinates. Or a typical example is, for example, Newtonian gravity that is invariant under translations, or maybe Einstein's field equations that are invariant under most general coordinate transformations. Now, that's all what I want to tell you about classical coordinates. And now I move to extension to it, which I follow here the ideas of Giacomini et al. Paper from 2019. But I'm going to read this paper in a different way, and this for the first time now. Namely, I will talk about, again, just two objects in the world. It's again a mass, it's again the Earth and the small atom. But now I will start from a certain coordinate system that I indicate this again with this hypothetical observer at the origin of the coordinate system, such that the state with respect to this coordinate choice look like superposition of the position of the Earth and maybe localized position of the atom. And now what I want to do is to move into another coordinate system, and this is the state with respect to this coordinate system, namely the coordinate system in which I will put the origin at the center of the Earth. And now I can ask myself, how should then two other objects, one which is just hypothetical, and the other maybe that is real, how should they look like in this coordinate system? And what we proposed in 2019, that they should get entangled, they should look entangled. And it's easy to see this because if you are in this branch of the superposition, then B is just right up and C is just right down, left down. So it's exactly these two positions of B and C. But if I'm in the right branch, then the B is left from me and C is even further away from me. So that's these two possibilities. And indeed, one can formalize this and introduce the exact unitary transformation that will change the state on the left to the right-hand side. And it looks like that. It involves A, C, and B systems, and it can be understood as A, you first read where A is, and then you push by the generator of translations the B to the extent where A is. And at the end, you just exchange C and A with this reflection symmetry. And indeed, if you do that, you will get as a final state a state that is entangled between the C and B, because how much you push the B depends on where A was. And that was the idea of this quantum coordinates or quantum reference frames. And again, you might ask yourself, well, what is this meaning of this entanglement between something which is a gauge degree of freedom and maybe some real systems? And I would say it's nothing else than what you have in the classical coordinates. It's imaginary coordinates that help you describe certain systems, but at the end of the day, you will concentrate yourself only on the physical degrees of freedom. And indeed, it's a helpful thing, because from something what on the left-hand side seems to involve a superposition of space-time, you get on the right-hand side with something which has a definite space-time. And now that's exactly the problem that I will want to investigate next, and to see if these tools can help me treat the situation we have a superposition of semi-classical spacetimes. And what I consider here is, again, in some coordinates, a mass to be in a superposition of two positions, and maybe a clock that is localized and think how this clock will now tick in this superposition of spacetimes. And what we, Anna Katrin, Victoria Kabel, and Esteban and myself suggested in a recently published paper in 2023 that we can go into suitable chosen coordinates such that something which looks like a superposition of spacetime go into the definite spacetime where we will be able to solve the problem with the conventional quantum field theory on a curved spacetime and solve the problem, and after solution go back. And the reason why we make this step is again the belief now that the physical laws preserve their form even not only under the usual classical coordinate transformations, but also extend to quantum superpositions of these coordinate transformation. And here is the sketch of this proof, and then I will go through this. Namely, we start with this situation in which the mass is in a superposition, the clock is localized, and then there is this hypothetical observer. And then via reference frame transformation, we, so to say, jump on the Earth or choose the coordinate system in which the Earth is an origin, in which case the two systems become entangled. Then we solve this problem, and we know that where we have now a clock in a superposition of two positions, that the ticking rate of this clock will depend how far we are from the mass. We can solve this problem with conventional quantum theory on a curved spacetime, and then go back into initial reference frame and provide the answer that was not immediately clear because we had to deal with the superposition of spacetimes. So how do we do that? Well, we choose this origin at the hypothetical observer. We have a superposition of mass, and then we have 2 degrees of freedom for the clock. One that tells me where the clock is, and the other is internal degree of freedom. This is exactly what is ticking. So it means that this internal degrees of freedom, it must be in some superposition of energy states in order to be dynamical, to tick. And in the simple case, these are just 2 energy levels. And then I move to another reference frame in which, as I said, the situation will be such that the 2 systems C and R will get entangled, and the internal degrees of freedom is still factorized out. And so we start with this system, and now we can solve this problem, for example, using some ideas from our group from 2011 of Zich et al. Paper, in which we have a single clock in a superposition of 2 positions, and then we see that the ticking rate will depend. The closer you are to the mass, the slower the clock is. And once we solve this, we can go back into initial reference frame. The way how we solve this is using this paper. Namely, you will see that there are 2 effects. One effect is the time dilation. So the pointer of the clock will depend on the proper time elapsed, which again depends on the relative distance between the clock and the mass. And there is another effect that is a cumulated phase for the 2 amplitudes, which again corresponds to the accumulated proper time. And so once we have this, we can go back to the initial reference frame or initial coordinates, in which now the mass is in a superposition, but the clock is localized, ticking in this superposition of 2 ticking rates. And inverse transformation brings me to the final state in which I have the effects of time dilation and the phase accumulated. Okay, so that's all what I wanted to tell you about one example where we apply this. And then the next, and now for something completely different, actually is not completely different. It will be related to quantum coordinates and indefinite causal order. And so just to remind you about the indefinite causal order, there is a series of works now, all already 10 years old, in which was proposed that quantum mechanical superpositions can be extended also to the causal order, to the situations in which we don't have well-defined causal relations between events, and we can speak about superposition where A is before B or B before A. The first explicit example was worked by Kiribedala et al. In an example of the quantum switch. And so far, we have been discussing in the literature 2 realizations of this indefinite causal order. One is due to superposition of trajectories in Minkowski space, and this has been realized here in Philip Walter groups, where you have in one branch a photon going first to A and then to B laboratory, whereas in the other branch it goes first to B and then A, and then we put this in a superposition, and the quantum switch means that we can apply, depending on the path, degree of freedom, which is the quantum control, the 2 operations in different orders on some target qubit. Another realization of that is in superpositional spacetimes, where the control is actually the large mass that can be put either closer to Bob or closer to Alice laboratory. And this mass will induce certain time dilation in the respective laboratories that is so large that the signal can travel from one side to another and come in time, so to say. And therefore, we have a superposition of causal orders. And again, if there is a photon or some other test system exchange between A and B, we can have a realization of the quantum switch unitary. And there is still going on a huge debate, what is the real quantum switch, optical or only gravitational? And I want to a little bit tell you about this question. And so now, having said previously that the choice of quantum coordinates can move you from the superpositional spacetimes into definite spacetime, so we can render the spacetime metric definite by quantum controlled diffeomorphisms, we may then ask ourselves, well, if the space metric determines the causal structure and can be rendered definite, maybe this applies also to the quantum causal order. Namely, can we always find quantum coordinates in which causal order becomes definite? Or can indefinite causal order be a quantum coordinate artifact that with the right transformation can be transformed away? And the answer to this question is no. And I want to convince you in the next couple of minutes that the answer is no. And in order to tell you, I have to tell you something about the work that has been done with Anne-Catherine, Victoria, Marius, and myself. I didn't put the citation, so I say it now. And for that, I want to introduce the general relativistic notion of the event and the causal order. First of all, think about these trajectories being the trajectories of Alice's laboratory, Bob's laboratory, and a test particle that is flying in between them. And now we define the events as the coincidences between the crossing points of 2 different fields, if you want. So interaction of Alice's laboratory with the test particle will be epsilon1, and Bob's laboratory and particle epsilon2. Now, what we will use to introduce the notion of the causal order is the proper time, also for the reasons that proper time is something which is diffeomorphic invariant. And we will orient this, parameterize the gamma 0 curve and time oriented such that time goes in positive direction from the initial point to the final point. And now we will use the proper time in between elapsed in between the 2 events, epsilon1 and epsilon2, to define the causal order. That's the way how we define the proper time. And I want already now to tell you an important element of that this proper time depends not only on space-time metric, but also on the trajectory. And we will see that in one case we make use of the fact that we put space-times in a superposition to achieve the indefinite causal order. That will be the case of the gravitational quantum switch. But in the Minkowski space, we can still make use of the superposition of trajectories to achieve the indefinite causal order, although the metric is always the same, and flat and Minkowski. And now, the exact quantity that we use for the causal order is actually the difference between elapsed proper time t2 minus t1, and more specifically, the sign of this difference. And then we will say that if this event is before the second one, then the sign will be positive by the convention how we oriented this curve. And if we have the opposite case, then the sign will be negative. Can you tell me? It's 10 minutes. 10 minutes, okay. So I will leave some time also for the questions. And now we will define the causal order defined by the sign of this S. That meaning that if it is a positive, we will say that Alice is before Bob, or if it's negative, Bob is before Alice. Now let me move into the superposition of the spacetimes. What I mean with this notation here, that in some quantum gravity theory, we will go into the semi-classical limit in which the states of the metric will be some very central, localized around some coherent states, and all the uncertainty around coherent states can be neglected, so I can really think about these two distinguishable and orthogonal states. Now, if we think about this superposition of two spacetimes, then we can associate to each the branch one manifold equipped with a metric, and also the sign of the causal order, and another manifold, again, equipped with a metric and the sign of the causal order. Now, the most important thing is that although we have 4 space-time points on the manifolds, they have little physical meaning unless we identify them with the coincidences between different fields. So if I think about the event epsilon 1 as being the crossing point of Bob's laboratory and the test particle, then I identify this point in one manifold with the same event, namely the crossing of the laboratory of Bob and test particle in the other manifold. So physically, these are the same or identified across the manifolds points, giving rise to just 2 physical points, although, of course, in each manifold, they are put at some arbitrary space-time point in one manifold and the other manifold. And now, after I identify these events, I can ask myself for each branch whether I have a positive or negative sign for the difference of the proper times. And so we will end up with 2 possibilities for the sign of the product of the time differences. If in both branches Alice is before Bob or Bob is before Alice, then the sign is the product is positive. But if we have an opposite causal order in the 2 branches, we will talk about indefinite causal order. And now we know that the proper time and that the sign will be, of course, invariant under diffeomorphisms. The thing here is an extension of this statement, namely that even if we use the quantum coordinates or the quantum diffeomorphisms, or in another way, if you apply different diffeomorphisms in different branches, the causal order will still be invariant under that. So there are 2 statements that I want to finish this talk, namely that in our view, there is no genuine indefinite causal order in the sense that gravitational switch is the real one and optical is not, because according to this definition in which we identify the same physical events in both branches, we in both cases have the property that the product of the sign is -1, and we have indefinite causal order. And furthermore, causal order cannot be rendered definite even by the most general quantum diffeomorphisms, namely those that, depending on some quantum system that is a quantum control, I can apply one diffeomorphism in one branch and the other diffeomorphism in another branch. For example, if I have in one manifold this situation and another manifold this situation, I cannot then map these points, A point, epsilon A point from one manifold and epsilon A point to another manifold with 2 different diffeomorphisms on the same manifold. And once I identify these 2 points, I will see that I will also manipulate the curves such that the indefinite causal order is preserved. And maybe it's really chaotical lines here, and you can't see, but I will drive you through at least just for one case. You can think about the black line as really this black line where I go from Alice to Bob's laboratory. But if I apply a different diffeomorphism for this picture, this will modify the black curve such that if you look at the black curve very precisely, it goes like that. So it goes first to the upper, to the upper lab, and then to the lower one, and then go out. So indeed, the causal order is reversed. And I'm coming with this to my summary. I want to remind you that we introduced quantum coordinate transformations, in which it was necessary also to have some gauge non-physical degrees of freedom. And by changing the coordinates, we succeeded in changing the superposition entangle between gauge and the physical degrees of freedom. But that was nevertheless useful in the sense that by assuming that physical laws preserve their form, even under this quantum coordinate transformation, we could solve some problems that could be, at the first sight, be problems outside of the regime of the well-accepted physical theories. For example, when we have a superposition of masses producing different ticking rate of clocks around them. And at the end, I introduce a notion of indefinite causal order, which could encompass both optical and gravitational quantum switch. And at least this shows that if you accept the gravitational quantum switch as the realization of the quantum switch, you should accept also optical. You either accept both of them or you reject both of them. And finally, we could show that indefinite causal order is invariant under these most general quantum coordinate transformations in which you can apply different transformation in different branches. And with this, I would like to thank you for your attention.
Thank you, Časlav, for your talk. I will open the questions with one question that was posted online from Samuel Fedida. Since the identification of points across superposition of manifolds is not unique, can you not find different maps of points that give you different orderings of events on a single manifold?
I would say that it is unique. It's defined by the events, physical events of the crossing between these two fields. And that's that. If I go back to the picture, there is no other possibility than identify this point with that point, because these are the two identical physical events.
Yeah, Thomas?
I have a question about the kind of principle of covariance that you use at the start of the talk. So in quantum mechanics, I'd say that there's, if your change of reference frame, if you change commutes with the Hamiltonian, then you have some principle of covariance. The Hamiltonian is the same before and after. So the same equation of motion. So I was wondering, why do you need this as an extra assumption? Could you just check that your unitary change of reference frame, which is this superposition, and commute with the Hamiltonian? And then if so, then you've shown that there's kind of a principle of covariance, right?
Yeah, I think this is the way how to do this. I don't know what I'll try to get, if I have actually something about that.
Yeah, exactly.
Exactly. So, yeah, so that, okay, this is the definition. So indeed, so I would say that you start with some Hamiltonian, let's say, from the initial Hamiltonian, okay, from the point of view of C, so the Hamiltonian is about A and B. We didn't have this very complicated situation so far, but I introduce now that it could be a Hamiltonian that involves all external systems. And then if this transformation is a time-dependent transformation, the Hamiltonian will change in this way. But if at the end I get now for another systems, B and C, the same functional form of this Hamiltonian, I would say this is a symmetry, and I would say this is then covariance is, or invariance of the physical laws is preserved. Yeah, I would say this is the most general formulation in Ham. Yeah.
So in a sense, it's not really like an extra assumption, because you can just kind of show that this holds.
You can show it's called, or it might be that it's not like that. Yeah.
Any more questions?
I may just add that sometimes it's very surprising things that if you start, for example, for the free particles on B, and you make a quantum translation, you will not get two free particles. So it's not trivial what Hamiltonians preserve this symmetry. Yes?
So, I obviously like a lot the last ideas because I'm a co-author on the paper. But the most general quantum theory, not really, right? Because we don't know what to do with the conjugate and so on. We don't know that it's the most general. That's a good...
Yeah, I don't know whether it's the most general. In the framework of what we do, which are the states of superposition of semi-classical spacetimes, it seems like then you really go branch by branch, and within one branch you can do normal diffeomorphisms. But if we go beyond this semi-classical approximation, I think there are more general transformation.
Any more questions? Yeah, I think then we can move on to our next speaker. Luca Apadula, who will tell us about quantum reference frame for Lorentz symmetry.
Okay.
Yeah. No, it will be mass. Nobody will understand the first part. Nobody will understand the second part. Sorry. We can put it somewhere here.
I can move, but I don't have to. Okay. How does it work? Like this, okay. Maybe like this is better. Oh, perfect. Okay.
I give you a 5-minute warning when it's 15 minutes.
Okay, right. Okay. Hi, everyone. So, thanks a lot for giving me the possibility to present one of my projects that I've done with my supervisor, Časlav Brukner, and one of my former colleagues, Stefan Castro. So, okay, Časlav already gave a wide introduction of quantum reference frames, so I will try to go directly towards the aim of our project. As you can understand from the title, quantum reference frame for Lorentz symmetry, we wanted to extend the quantum reference frame formalism in order to incorporate also Lorentz symmetry. So you can consider special relativity as the framework stem from the Einstein operational approach to space-time, which is based on how clock, ticking rates, and Lorentz transform between inertial observers, right? So the first question that one could ask is, okay, what happens if then we extend the quantum domain to inertial observers, no? So, well, like simply one could ask what happens if I consider, for example, a superposition, a Lorentz observer in a superposition of velocities, so how this observer would perceive then the physical world. Then more precisely, how then would be the implied geometrical structure that comply with this extended notion of covariance, okay? So, okay, the next slide is a bit formal, but the only thing that I want you to enucleate from it is that first we wanted to use a covariance formulation of quantum mechanics, which has been already introduced by Carlo Rovelli, if I'm not wrong, in the 90s. It's a bit different, but it's basically very much alike. In order to avoid to refer to any preferred notion of time frame, we wanted to have a picture where time and space are treated somehow symmetrically in order to somehow better fit the requirements of Lorentz symmetry. So we incorporate somehow space and time coordinates in this so-called space-time cat, okay, in this way, where E of p is the positive square root of the relativistic energy. And then by linearity, we define so-called space-time quantum state. I forgot to say that we reduce the space-time to 1+1 dimension. And these generalized relativistic quantum state allow us to simply to extend somehow the initial condition of a state. We don't give a state lying on a simultaneity surface, but we can somehow localize the state in an arbitrary region of space-time. For example, in this moon-shaped region, which is basically the F support. Now, a few features of this formalism. If we do the pairing of these two space-time cats, we get the propagator for positive energies. Then if we project on T prime X prime the space-time quantum state, we get the standard notion of a relativistic wave function, which comply with the positive square root of Klein-Gordon equation. And we recover also the standard Klein-Gordon inner product if we do the inner product of these two space-time quantum states. Maybe the last thing is, okay, how these space-time quantum states behave under the action of a general Lorentz transformation, and they behave exactly as we could expect. The space-time coordinates transform accordingly to the Lorentz boost, so they are hyperbolically rotated. Okay, so if we jump on top of this flying rocket, what we would see is this hyperbolically rotated, boosted, moon-shaped region of space-time. Okay, and now in this slide I will try to briefly explain how we build this prescription to jump from one relativistic reference frame to another, from one system to another. Okay, we have to keep in mind that one mantra of quantum reference frame formally is that every physical meaningful statement is relational. So, in a very simplified example, I'll give you a state describing my physical landscape, free particles, okay? And this is given according to one Lorentz perspective, okay? But I want to achieve a fully relational description in order to describe one particle with respect to another system, for example. So we achieve this sort of fully relational perspectiveless state formulation, simply making the state invariant under the action of global Lorentz transformation. From a group theoretical point of view, this means applying the G-twirl of the group, so integrating all over the possible Lorentz transformation of the state. So now we have this Lorentz perspectiveless formulation of the state. And then what do we do in order to take the perspective of one of the internal system, one of the particle, for example, C particle? More or less as Časlav explained, we have this control Lorentz transformation on the state of C particle. We read basically the state of the momenta, and then the velocity and rapidity, and then we transform accordingly the rest of the systems.
Sorry, this integration that you're making, does it converge? I mean, it's not compact, no? This group, or?
No, it does converge. It does converge, yes. Yeah, at least for one-dimensional 1+1 space-time, I'm quite sure there's a result that says that.
What are you integrating there?
On the rapidity. Okay. Rapidity of is the parameter of the Lorentz boost.
From 0 to infinity,
minus infinity plus infinity.
Okay.
Yeah. I mean, but yeah, no, but. Right. So what we get from here is the state from the perspective of C. Interestingly, the interesting thing is that the state of C now is factorized out, so there's no relational quantity between C and the rest. And we can simply trace it out, to give an intuition that there's no somehow mathematical physical content in it. Omega C is simply the full superposition all over the possible momenta of C, so basically full indeterminacy. And we can do the same for A, no? So then the transformation that would guide me from C point of view to A, it's simply the suitable composition of those maps, which gives us back exactly what Časlav presented before. Okay, so now we have the mathematical tool that would allow us to jump from C to A, from one relativistic quantum reference frame to another one. And then let's apply it to simplified scenario. Okay, so now we have a state from the perspective of the guy sitting on the ground, describing a rocket in a superposition of sharp value of velocity, for example, and FB space-time quantum state, describing this moon-shaped state, okay? And now we're going to jump on the rocket, and what we can get, as we somehow could expect also from Časlav's presentation, is an entangled state, where in each branch we have a different boosted moon-shaped region, okay? Now entangled with the previous relativistic quantum reference frame labeled by C. Okay. Another somehow interesting example, somehow which refers more to a standard case where we somehow locate the state in a simultaneity surface of C. What happens if we perform the jump is that there is a resulting state. We have a superposition of tilted space-time slices, which are not anymore simultaneity surface for the rocket's pilot. Right. Okay, another feature that is worth to be discussed is the analogy, what comes from the analogy of active and passive representation of the transformation. We can picture in the active wave this state keeping fixed somehow the space-time frame and having the superposition of the differently boosted moon-shaped region, or equivalently, we can keep fixed the space-time volume, this moon-shaped region, and express the superposition in terms of the space-time frames, right? Okay, and now these are the last two slides. Here, we try to recover the standard phenomenology of special relativity. I'm good with time, perfect. So the scenario is basically the same. Okay, we describing this physical landscape from the point of view of the guy sitting on the ground. We have a couple of point-wise events, which according to this guy, they have a separation in time of delta t, t2 minus t1, okay? And now, what happens if we jump on top of the rocket? Okay, now we don't consider the entangled state, the state of the reference frame C. We just focus on the state of the clocks. We have an entangled state. In each branch, we have a boosted couple of the previous event B1, B2, which now have a time separation, which is a special relativistic time dilation, okay, according to the gamma factor for the blue branch, gamma of omega pi 1, which is related to the velocity of the blue space shuttle. And the same thing for the other branch, okay? So we can infer basically that the rocket's pilot is observing a superposition of special relativistic time dilations. And then we can basically say the same for the length contraction. Okay, now somehow the setup is a bit more cumbersome because of the complication of performing a measurement of rod lengths. But basically, it's very similar. Again, we start from the perspective of C. We have two couple of point-wise events, moon-shaped and atom-shaped, which they have a space separation which coincide with the length of the rod of the guy sitting on the ground. And now the velocity of the rocket is related to the ratio between the space separation delta TB over delta X for VB, and delta TD over delta X for VD, for the yellow speed, okay? And this is why, because once we perform the jump, we're gonna obtain in one branch of the entangled state a couple of events which lie now in a simultaneity surface for the rocket's pilot. So we can somehow perform the measurement of the length, which is going to be a spatial relativistic contraction of the rod length of the guy sitting on the ground, and the same for the yellow branch. Okay, so also in this case we can infer that the rocket's pilot probes a superposition of spatial relativistic length contractions. Okay, so this is basically all the somehow extended phenomenology that we probed with this in this extended framework. So let me summarize a bit what we did. We started from the basic question of like extending what we know about Lorentz covariance if we allow an inertial observer to be described by a quantum state. First of all, we use this new picture. Okay, it's a different picture for a relativistic quantum system, which allow us to have this general space-time representation of the state, not referring to any preferred time frame. And then, thanks to it's called sort of quantum Lorentz transformation, we can perform this change of perspective, obtaining all the consequences that we already seen. So superposition of space-time frames in a sense, superposition of spatial relativistic time dilation and length contractions, okay? So this is basically summary of this work. And then for future prospects, this is basically one small piece of work which is cast in a choral somehow effort, no? As Časlav said, in order to better understand the interplay between quantum mechanics, quantum domain, and space-time geometry. An interesting thing would be somehow to give a complete prescription of what could be a sort of quantum chronogeometry, no? What would be, in geometrical sense, what would be the geometrical structure which has this extended notion of group of symmetry group, sorry. And of course, another interesting thing will be to extend this framework to a field scenario. And this is basically everything that I wanted to tell you about.
Thank you, Luca, for your talk. Are there any questions?
Sorry, I'm not too familiar with these problems about covariant quantum mechanics.
Right.
So maybe ask you a question to understand that.
Yeah.
So you said you localize the state at a given time, you have the clocks, for example. Exactly.
Yeah.
What does it mean with the thing on the right exactly? Like, what's the operational interpretation from the point of view of the guy on the rocket?
On the rocket, it means that if you boost at a simultaneity surface, this is not going to be anymore a special slice, but it's a space-time slices. It's not what is a simultaneity surface for C is not anymore a simultaneity surface for the guy sitting on the rocket.
Yeah,
no.
That I understood, but operationally that quantum state, so it's supposedly that picture represents a quantum state.
Yeah, right.
So what does that tell us about the measurements the guy is going to do?
Ah, okay. These are the thing.
About this formalism of the random.
Yeah, I mean, it's simply, you can maybe better think as a sort of state preparation, no? I make a state preparation which lies on a simultaneity surface, okay? So, like zero spread in time and completely spread in space. And if I'm gonna boost this basically means that this state preparation according to the rocket point of view is gonna be distributed in a tilted space-time slices. So yeah, it's, I don't know if I answer your question, but it's more or less how I would interpret this.
Maybe it's related with this question, but isn't that then all the blue clocks should mark the same time and the yellow clocks also the same time?
And no, I mean, okay, maybe it's a bit idiosyncratic, this picture, but it's just to
maybe it's just a representation.
yeah, it's just to show that it's not anymore a simultaneity surface.
Yeah,
it was from
C.
So
they all should,
exactly.
if those are clocks in C,
No, but it's not really like a clock system. It's something.
Marking the time of the guy.
Right. Yeah.
You have been thinking about this, so this is, I wanted to ask how to phrase this. So usually when they teach us like field theory in, university and so on, the way they go about it is that they first teach it to you as a symmetry, like the Lorentz group as a global symmetry.
Right.
So you do it briefly.
Right.
And then, you learn to do it locally. You just put the next dependence on the group action. So what is we look at the natural next steps and how you take this story and you say, well, this now is happening
Right.
at that point. What is the technical difficulty in doing that step?
Oof. Okay. But you're saying something in like to apply this in a sort of curved space-time in order to extend this local symmetry to something.
This is a global symmetry.
Yeah.
And you make it local.
Right.
First step towards GR.
Right. Okay. The difficulties that would arise in that case. Oh, okay. Yes, I have to admit that I have no idea which kind of difficulties you would encounter in that case. You don't even dare, no? To think. No, I don't know. Now, if I have to reply really right now, I have a bit of frozen brain. I am not able to reply, but I can maybe.
So it's something to think about.
Yeah, it's something for sure. No, yeah, sure. Yes.
Yeah, a short one.
So maybe
We can also discuss later.
Maybe you can just
my
discuss
question
later.
is based about this. You are constructing this based on like relativist quantum mechanics,
Right.
but I mean that's something which don't really exist, right?
Right. This is why I was talking about the field scenario, because
So
there's no.
The question is, does that introduce some limitation?
Yeah, sure. Yeah. You have all that series of problems that you have for one particle sector. Yeah. You have all of them. Yeah. You're not gonna solve any of those problems in a sense. No.
Yeah, I think we have to proceed to our next speaker. But let us
Okay.
thank you.
May I take this?
If you want to sit here, you're not your head is not going to be on top, so you can't sit here.
So our next speaker is Veronika Baumann, who will tell us about different perspectives in non-causal quantum processes.
Okay. Thanks, Stefan. Okay, so I'm going to present this joint work with Marius Krum, Philippe Alaguerin, and Časlav Brukner, which is more on the indefinite causal order side of things here. So I'm not going to talk about space-time unless in the context of motivation. I want to start by briefly specifying what quantum processes are, and we introduced the notion of causal reference frames, which are not the same as quantum reference frames. This is a kind of a name confusion, but this came about first, and is in the context of process matrices. Then I'm gonna briefly talk about the Papageorgiou's formulation of quantum circuits, and finally going to tell you about what we did in the paper and what we call non-causal Papageorgiou circuits. Right, so the process matrix formalism is about so-called quantum processes, which are generalized higher order quantum maps. So they take quantum operations as input and give another quantum operation back. And the interesting feature about those is that they are potentially what we call non-causal, meaning that they are incompatible with a definite global order of the operations they take as inputs. So if you want to talk spacetime, you can say there is no notion of a well-defined global time. Specifically, we were looking at pure processes because those are the ones that are believed to be physically relevant. And the pure process G, which takes as input these operations, is a unitary whenever the operations are unitary. And they are physically interesting because they reversibly map a global causal past to a global causal future, which was shown in this paper here. So, suggestive picture, if you think that these operations are performed by these little agents inside their sealed laboratories, at the beginning of everything that's described by this process, there is a well-defined notion of time that passes for all the agents involved, and some global input state psi. Then there is some weird stuff happening in between where you cannot define this global time. But at the end of the day, they all come out again, time passes equally for all the agents, and this map G, which is, again, a function of all the operations that these guys have performed, has been applied to this global input state. If I now want to talk about a perspective of one of those agents inside such a process, I want to look at something like this. So I imagine that inside this laboratory, there is a well-defined notion of a local time for this agent. So he or she can tell how time passes for inside her lab, and that at some point she will have to apply the operation, which we then consider as her plugging in her unitary into this generalized box that describes the process and is a function of the operations of all the other agents. Right. Then causal reference frames were introduced in this paper here. And they are basically the perspectives of these agents inside a process in a very general way. The key insight there was that you can decompose any pure quantum process as follows. So I'll do the two-party example. It, of course, generalizes to arbitrary many parties. So if I have a two-party process, I can write it like this, such that the one unitary I'm interested in here appears in the middle and nothing happens to the rest. And then there are two other unitaries, phi A of that then depend on B, and a pi A of B, which are called the causal past and causal future of Alice. So since Alice appears in the middle, this is her causal reference frames. So she has a notion of when or that she applies her unitary at some point. And there are other unitaries that describe the happening around her. And this is, in general, since these quantum processes are formalized in terms of quantum info and circuits, these are perspectival circuits. So for Alice, this process looks like this. Her operation appears in the middle, and there is some past and some future for her perspective. And then I can do the same for Bob. So I can just write down another decomposition of this process where now Bob appears in the middle and has, of course, again, a causal future and a causal past that now depends on Alice's operation. Which means that I have a different circuit here where Bob appears in the middle. And all that was required in this original paper was that at the end of the day, those two describe the same process in order to be compatible. Right, now, completely different subject, but we need it for what happens afterwards. The Papageorgiou's formulation of circuits. The Papageorgiou's formalism is, well, a version of relational dynamics. So I have a constraint equation for the joint system of some clock and the system I'm actually interested in. And I say the physical states, these double cats here, are the ones that satisfy the constraint equation. And then what was the original motivation of this Papageorgiou's thing is that they can show that I can recover time evolution in this static state via the correlations between the clock and the system. And this has also been formalized for quantum circuits. Well, for example, these papers here. So if I have a circuit like this, and I want to describe it in terms of a Papageorgiou's state, what I do is I append a discrete clock that now performs a finite number of ticks, and such that whenever the clock ticks, one of the unitaries of the circuit is applied, and then I can write down a Hamiltonian, and then I see that my physical states look like this. So I have a normalization factor in front, and then I have this sum of all the possible clock states, and whenever the clock reads a certain value, I have here the state of the circuit up to this point. Good, now we wanted to do something similar, but not with one clock, but with multiple ones. Namely, we wanted one clock for each agent in order to account for their local time in this Papageorgiou's picture. So now we have a state that lives on, well, the clock Hilbert space, the system Hilbert space, and we have some ancillas there for purification to be able to work in this pure setting. And this clock space now consists actually of many individual clocks. And then I get a physical state that, well, looks rather messy, but I have a sum over all the different clock values that start from 0 and range to some final time t indexed by the agent I'm looking at. And here, for every combination of clock readings, I have some conditional state on the system and the ancillas. What we then said, okay, now we want this state to describe well, potentially non-causal quantum processes, quantum process. So what should it look like? Okay, we wanted it to start out like this. So I have all the clocks initialized to 0, some global input state, and some reference state on all the ancillas. And what I want at the end is that all the clocks read their final value, and that this process that I want to describe via this physical state has been applied to the systems and the ancillas. What we also put in there for cosmetics was that we want one synchronized tick of all the clocks at the very beginning and at the very end. Because, remember, we wanted to describe something like this, where at the beginning and at the end of our scenario, we have a well-defined notion of time. So now we have something like this. The weird stuff happens in between. At the beginning, all the clocks perform one tick together. And at the end, all the clocks perform one tick together, and nothing happens to the system anymore. Good. Now, the nice thing about this Papageorgiou's formulation is that you very naturally get a perspective by just projecting on the clock you're interested in. So if I now want to describe the perspective of agent X, I just project at a certain time. I project on that clock that is associated with agent X to read time tx, and then I get this perspectival state. What I need to put in this normalization operator here for technical reasons, which is, well, a priori, it is just any operator that acts on anything but the clock, but we introduced additional physically meaningful axioms that would make sure we cannot do anything, like everything with these operators. They are just a generalization of renormalization factors. Then these perspectival states are unitarily related, and this UX is basically the perspectival evolution that this agent sees inside the process. And what we also required is that there should be a well-defined, what we call time of action Tx, where, inspired by the causal reference frame, where this agent applies his or her unitary and the rest evolves in some uncorrelated way. So we wanted to describe this picture, and now we are aiming for something like this. So we have now explicitly incorporated how time passes for the agent, and that this time is when she plugs in her operation, right? Good. So far so good. So we managed to do this and write down some interesting states, actually. And what we found in particular is that these perspectival states are somehow a refined notion of the causal reference frames, which we were kind of aiming for and managed to do. So it's basically causal reference frames with additional information how the time passes for each agent. What it was also nice is that you can already have some non-trivial perspectives for causal processes as well. And probably the most interesting part is that the fact that now the perspective has to all come from this one physical state introduces some constraint on what they can look like. In particular, there is this criterion that we call affine linearity that says that the perspectival unitaries for each agent can only consist of terms that are either linear or constant in all the operations applied by the agents, which is a pretty severe restriction and which will become relevant towards the very end again. Good. For example, we did something that we then termed the twin paradox circuit, suggestive name, nothing else. So we were looking at a causal process, a bipartite one that looks like this. So Alice acts first, then there is some joint evolution, and then Bob acts second. But now, so we have a circuit like this, but we wanted to capture a scenario where time passes differently for the two agents, just like in the twin paradox scenario. So for Alice, this circuit looks like this, but her clock ticks like that, and she has whatever time of action. The same for Bob, but for Bob, time passes faster. And you can do this by writing down this beast of a state. Never mind the details, but we have basically here this synchronized tick at the beginning and at the end. And then here we have terms where Bob's clock just ticks twice as fast as Alice. And for the individual ticks, the different parts of the circuit are implemented on the system. Now, the more interesting part appears if we go to non-causal processes. But well, there is this hand there. Never mind. So the simplest example is the quantum switch, which Časlav already briefly introduced. So we have a control, and depending on the value of the control, either A acts before B or B acts before A. Good news, you can relatively easily write this down. Again, never mind the details, but let me tell you what happens here in this state. So again, we have our synchronized ticks at the beginning and at the end. But then how we implement this process is as follows. So first we have this green, what we call a desynchronization step, where depending on the value of the control, we initiate different clock orderings. So if the control is 0, Alice's clock runs ahead of Bob's, and with 1 it's vice versa. In the middle, we have this part where both agents apply their unitary operations. And then at the end, we have this resynchronization step, which is basically the inverse of this, where depending on the value of the control, we slow the clocks down individually such that they, at the end, read the same value again, and then this process has been applied to the system. If you look at this state and then do the projection and write down the individual perspective, you get that Alice's perspective corresponds to this circuit, with her time of action being 4, and the same for, or very similarly for Bob, you get this type of circuit with the same time of action. And these circuits, these two perspectival circuits, are exactly the ones that were given as the causal reference frame decomposition of the quantum switch in this paper here. So all we have now is a more detailed description with information about how time passes for the two agents. What we also showed in the paper is that you can do this for any type of coherent control of causal order, by which we mean a general quantum process that looks like this. So I have a control system that runs over a finite range of values, k, and for every k, a different causal process, g tilde k, is implemented, and at least for 2 of them, the order is different. Then I have a non-causal process that is an example of coherent control. Well, it's super ugly, the general procedure we wrote down, but the important part is that it works exactly like the switch. So we start with a desynchronization step, where depending on the value of the control, we implement different orders. Then we have these application terms, where just each agent applies their unitary. And then we have a resynchronization step, which is the inverse of that. And then again, end up with all clocks reading the same time and the process having been implemented. Good. Now the bad news. Not all pure processes are coherent control of causal order. For example, this one, the Lugano process, is a pure non-causal process that is not coherent control of causal order and that is also known to violate causal inequalities, which make it very interesting. So it's a tripartite process that looks like this. It doesn't matter too much. But it's basically the simplest pure process that is known to violate a causal inequality. And we tried to implement it, but couldn't. And one reason why we probably couldn't is that there is a problem with this affine linearity requirement that we got from the Page-Wouters formulation. Namely, if you look at the causal reference frame decomposition of this process, that's also given in the paper I previously mentioned, it looks like this. And as you can see here, these gates, so this is A's perspective, right? She's in the middle, and then there is a causal past and future depend on B and C. But these gates here are clearly not linear or constant in the operations of B and C. And it's the same for every permutation of the agents. So this perspectival circuit can definitely not appear as in the Page-Wouters formulation. However, the causal reference frame decompositions are not unique. So this, although we know this does not work, it is not a definite criterion that says that we cannot at all, under any circumstances, implement this process. So far, so good. That's what we did in the paper. And what we want to do now, well, is in this paper, we have also only looked at potential physical states that basically do what we want them to do, right? So now we want to look a bit more into the whole Page-Wouters stuff, write down the constraint equation, see how the changes between the perspectives should look like, and especially whether this suggests any further requirements. As we see, as I said, this affine linearity thing came out just of writing down the state and was pretty strong, right? So we hope to find more requirements there that rule out certain processes and then maybe allow us to give a definite answer regarding the Lugano process. Or if not, how can we implement the Lugano process? What do we need to do in order to write a Page-Wouters state for this one? And once we have a sort of answer to this, what about causal inequalities in general? Is there a Page-Wouters formulation that tells you how to do basically processes that violate causal inequalities? Or does this formulation suggest that processes that violate causal inequalities should not be considered physical, which would also be an interesting answer? And with that, I thank you.
Thank you very much for your talk. Do we have questions? Yeah, Markus?
Quick question. So thanks for the great talk. I really enjoyed it. I wonder, so I understand that you can build it in a way so that sometimes A's clock runs faster and sometimes B's, for example.
Yes.
So what are the rules of the game that you say? I suppose you cannot run one of them backwards, for example.
So exactly. So yeah.
Does it follow from this?
It doesn't follow. So the thing is, for the Lugano process, we thought about, can we run one of them backwards because there is, sort of description or understanding of the Lugano process in terms of closed time-like curves. It's a mess. I mean, it is. So naturally, what you would write down as a clock and how you, extract the information out of the state gives you a well-defined notion of time, right? You just project it, but from the way you read it, more or less. If you want to have something run backwards, this is not at all straightforward to do or see in Page-Wouters. You could start thinking about some general that the time is circular by definition, that the Hilbert space is such that you run around the circle. But then it gets very, very ugly. So if you otherwise want to kind of force the inverse perspectival evolution, that's what people in Zurich have tried. It also gets complicated and normalization gets highly non-trivial. It gets ugly very fast. So if you really want to do it, and it's, for me personally, it's always not clear whether this is really the clock running backwards or you just doing something weird with a state that doesn't actually tell you that.
sorry, I didn't understand it all, but I think it was an interesting talk, the part I could make. So also, I know the circuit part, right? I mean, the part
Yes.
of the code to computing, right? I mean, it's like you simulate a circuit and then you make a Hamiltonian. And then the ground state is actually somehow simulation of the circuit.
Yes.
So can you do kind of similar thing if I give you like a process, like, okay, I made a Hamiltonian, and if it has a zero ground state with zero energy, right? I mean, then you know how to model it. But could it be that it does not? In which case you could argue that it's
yes.
really a physical
This would, yes. So we haven't explored this, but this was an idea we had at the very beginning. If we then said you cannot satisfy the constraint equation, this clearly, it's a good argument for you saying that, okay, this process is clearly not physical in that sense.
Oh, okay. But you didn't manage to discard any in this argument?
And we didn't look into it, so we don't, I mean, you know, you need to, this was not, in anybody's expertise of the authors of the paper, let's put it like this. So this circuit to Hamiltonian reconstruction is its own machinery, right?
Yeah,
and
it's like you have like a series of constraints, you put them all together in some way, and then if there's a solution with zero energy, then you know that they can be satisfied simultaneously. So that's why I'm thinking that maybe...
yeah, maybe there is a simple argument to be had. So the first idea was to actually look at it, but then we thought, okay, so yeah, who wants to do it? And then nobody raised their hand, so we didn't. But yes, maybe you can just make a general simple argument. I might want to look into that. Thank you.
I think we have time for one more question. There is one. Okay, then.
Everything's clear.
So what do I do with this? I just... Good.
You're discussing with
You do 5 minutes warning.
Perfect.
After 15 minutes.
Perfect.
And you have to point it a bit at the
And?
You point it a bit at the
5 minutes before 20 or before 15?
Before 20.
Okay. Can you give me also 5 before 15?
Then I do this?
Yes, and perfect.
Our next speaker is Eleftherios-Ermis Tselentis, who will tell us more about the Möbius game and other bell tests for relativity.
Okay, thanks, Stefan. So I'm going to talk a little bit about our new work with Armin Baumeister. And so what is this about? The idea behind this project is, so can we set up an experiment such that certain observations can be termed incompatible with any explanation or description coming from any theory that assumes what I call a fixed causal relations, and what would be the physical interpretation of it. Now, by fixed causal relations, what I mean, there are different ways. If I am to put a little bit of ontology on top of it, I think people call it fixed background or static spacetime. I'll also refer to it, all of these interchangeably. So the first thing I want to do is actually, what is this property? I want to phrase it in a device-independent way. That means I want to pinpoint exactly what is this property as a constraint that I will, as a decomposition of probabilities that of possible events in agents in distant locations, right? And that I call static spacetime, and that will be the partially ordered correlations. The second thing, I will go directly to the results. I will present these Bell tests for this. And finally, I'll go to the third part, which is the physical interpretation a little bit of this. So the first two are just mathematics. The maybe important part is the third one, the relativistic discussion. And I will end up with conclusions and open questions. So going to the first one, what is a static spacetime in a device-independent approach? So two events, let's say, can have possibly, I cannot move much, can have possibly two, they can be either time-like or space-like, and they can be time-like, for example, A before B or B before A, right? And when they are space-like, actually these two decompositions hold simultaneously, which means I would just throw away some of the dependencies to make them
look the same. So how does a static spacetime, how does it look as a decomposition, as a constraint? That would look like this, right? So I have one case where A is before B. You see here the output of A depends only on its input and not on anything else. And here also, the B is before A, so it only depends on its input, like here. And has been studied, I think, to my best of knowledge, 2012 was the first time for this. We're gonna do the very general decomposition we are studying in this. I'm not gonna go through the details of what this is, but you can just see the figures and maybe have a way. So what are the Bell tests? So the question is, how do we certify that a certain probability distribution cannot have some decomposition, right? So these are some tools that we already have from quantum information and from quantum foundations, right? So we find, I think this went bananas. Okay, sorry for that. Right, so we find the facets, namely a set of linear inequalities, such that if any of them is violated, we know that a certain probability cannot have this decomposition. Right, and how do we find the facets of this partially ordered polytope? Actually, we reduce it to another problem, and we harvest the results from there. Just a few comments on that. This problem was studied by theoretical computer science in the beginning of 80s, more or less. It's called the acyclic subgraph problem, and I'm not going to go into details, but it's interesting, actually, that it has been studied in a completely different context. So actually, we can harvest all the results from there as soon as we reduce the problem, which we do. So what are the Bell tests? So we're going to actually, there is a very natural way of phrasing these games, right? These facets of the polytope, if you want. And we are going to encapsulate or encode this into what we call the Bell test graphs, right? Let me read a bit this, and I hope it will become clear. So let's say we have n parties, and we have one of these Bell test graphs. That is some set D with some vertices V, K, and some edges, EK. So the game is as follows, right? A referee picks at random an edge from this Bell test graph, right? An edge defines a sender and a receiver, and some random bit B, 0, 1, right? Then the referee announces who is the sender and who is the receiver to every party, right? And distributes B only to the party S, to the sender, right? And the parties win this game whenever the output of the receiver equals the bit that was distributed to the sender, right? Now, as I said, now this doesn't hold for any graph. The ones that certify as Bell tests, so the ones that certify for Bell test are very specific topologies, are very specific directed graphs. And they have, like, in the literature, there is at least 8 families of different, very interesting directed graphs that can certify as Bell tests for this one. I'm going to present, I don't have time, so I will go only through one, the cycle graph. And maybe I can also run through an example to see how does this work. So let's say that we have 3 parties, and they are wondering whether whether they're incompatible with the assumption, whether their observations are incompatible with the notion of a static spacetime, right? Right. And they will play this, what we call for k equals 2, a 2-cycle graph, right? So how does this? I will just read from here, right? So a referee picks at random an edge from this graph here, right? And a bit. That would be, for example, let's say in this first round, it picks the edge A to B and picks the bit B equals 0, right? That means that, and continue, then the referee announces that to all parties. That means this is the input to all parties, and B is the extra input to the sender, which is Alice here, right? Then the parties win the game whenever the output of the receiver equals the bit that was distributed to the sender. So the receiver is B here, and if the output is 0, same with B, then they win. and so on and so forth. I can run a second round here also. Let's say that they chose the other edge. The referee picks at random an edge. Let's say that it picks the other from B to A. And a random bit, it picks B equals 1 for this round, right? Again, B is the receiver, the sender, sorry. Therefore, it gets also the information for the bit. The rest of the parties only get the information who is the sender, who is the receiver. And they win this round if the output of the receiver, which is Alice in this round, equals the bit B, which is 1. And so on and so forth. And at some point when they have enough statistics, they say, okay, are we incompatible with or is it inconclusive, let's say, like the test. So if they find out that the probability of winning this game is more than 3/4, then they have certified that they're incompatible with the assumption of static spacetime here, right? And this you can generalize for any k, actually. So this is the general formula, and this for k equals 2 comes to this. And let me say that indeed exactly this game, the bound is violated by the 4-party unitary quantum switch process. Right. So there are, as I said, there are many families of these bell test graphs, one of which is the cycle graph. Another interesting is the Möbius graph. We have analyzed 3 in the paper, but as I said, there are around 8 very interesting, which we don't see actually what are their components. I mean, why the new thing that these graphs introduce is, for example, non-planarity. Actually, the fact that you cannot draw this graph in 2D without edges crossing, right? This is the new that this Möbius graph adds, which doesn't have the cycle graph. But it's, yeah. So that's for the bell tests, right? What about the violation in the process matrix formalism? Let me quickly just say that we show that we can violate them for any finite number of parties. And the processes that we show that can violate them, they have the following properties. They're classical and deterministic, and they always produce causal correlations. This will be important for the physical discussion later. Let me go to the perhaps more interesting, the physical part. How do we interpret all this mathematics, right? So we want to exploit these bell games to make a distinction between special and general relativity, right? And how do we do that? Yeah, in essence, these bell games, what they tell you is that if you have, if your events are partially ordered, then you have certain limitations on the correlations that you can observe, right? So the definition of what an event is very important and crucial to the physical interpretation that you want to have. So in order to make the physical distinction that we wish to make, which is distinguish between special and general relativity, we use accept the notion of event, which is the crossing of word lengths. Right, so let's see the setup. What do we have here? We have Alice, Bob, and Charlie in this space-like surface, and we have many referees. Let's see what they do. So R0 is the one that carries the inputs to the parties. For example, some encrypted light signals. So as soon as R0 meets here with Alice, gives her the input, and so on and so forth. Then we have all the others, let's say they travel close to the speed of light, and make sure that the outputs of the parties are timely produced, right? Because you see here, when row 1 meets with row A, this region ends in some sense, right? So these are some causal diamonds, right? That they are the intersection of the future light cone of this point and the past light cone of this point, and so on and so forth. And each event for each party happens within these regions. And by definition, actually by construction, the way that we have made this scenario, the correlation of these 3 events, one for Alice, one for Bob, and one for Charlie, they are partially ordered, right? By definition, so no inequality can be violated in this scenario. What about GR? So the bell games presented here are won with classical and deterministic processes that produce always causal correlations. That suggests perhaps, we haven't done this calculation, that's why I'm speculatively phrasing this, maybe one within general relativity, and likely not with something very exotic, let's say, right? With globally hyperbolic spacetimes, hopefully. We don't need something exotic here, right? For example, we could play in this scenario that I presented, we could play this two-cycle game, right? Alice, as soon as she gets her inputs here, right, and knows whether it's going to be Bob that, sorry for this. So for example, Alice, when she receives from A0 the inputs here, it's going to be either B that has to signal something to C, or C that has to signal something to B. If it's the latter, C has to signal something to B, then Alice may alter the space-time structure within her future light cone, right? Depending on the announced edge that she receives in this region, she could displace a heavy mass, let's say, right, that will invert, compared to the relativistic scenario, the causal relations between these space-time regions, allowing the transmission of signals from that region to this region. And if the probability is more than 3/4 in this game, they have certified their inconsistency with a static spacetime and therefore with special relativity, right? So for example, this would exclude any possible explanation or description coming from special relativity. So let me recap a bit what I said. The point that I wanted to make for this, the whole project was whether we can set up an experiment such that certain observations can be termed incompatible with any description or explanation coming from any theory that assumes fixed causal relations. Fixed background, static spacetime, all these are the same, right? And what would be the physical interpretation, right? I pinpointed this property in a device-independent way. We sort of solved this problem and presented you some of the Bell tests here, and a little bit argued about hand-wavingly about the interpretation and how we can make it happen. And I have many open questions, but I only will phrase one. So the detection of this dynamical causal structure, right? So if we see a violation, can be understood as the detection of curvature change, right? In the GR language. So if we were to see violation of this, we can interpret it in GR as saying like we have seen the curvature change in a spacetime manifold. So the question is, to what extent can these games detect gravitational waves, for example, or and what is the precise general relativistic description of these objects that violate these inequalities, right? And I think that's that. Thank you.
Yeah, thank you very much.
So the way they are thought related, you only distinguish between static spacetimes to evolving spacetime, not from flat to curved, right?
What was the second? Static to?
Evolving. Static to dynamic.
To dynamic, yes, exactly. To adaptive dynamic, exactly. Yes, yes.
So is there a way to parameterize the inequality so that you can parameterize them according to how the curvature is changing? Say for a very simple
yeah, that would be very interesting, but I guess that would first have to come through the step where you actually interpret, like the third part where I did the physical discussion, the interpretation in relativistic. One has to really sit down and do the calculation, and it's not really about the difficulty of calculating, it's difficulty about putting the concepts together, right? But indeed, that would be ideal, for example. Try to parameterize, try to see, because there are many different inequalities, right? So which one, there might be stronger, right? Less stronger. Indeed, to give you just an example of differences between these inequalities, right? So here, this one is much stronger than the cycle inequality, the Möbius. Okay, obviously it looks more complicated. Yes, but for example, this one has an upper bound of 11/4. The game bound is 11/12, sorry, 11/12. And you can actually see that you have unlimited, you can always violate for any finite number of parties, you can always violate this. So that makes it somehow a robust test. This is also the case with quantum non-locality. You have cases where you can always violate. Yeah, so I'm not really answering your question. I'm saying that it's very interesting and I have no idea how to do it, but it has to go through this yeah.
However, even within the formulation for this, they have this certain inherent detection efficiency, right? But these tests have to run in a certain short amount of time. Say if Alice is pushing this big mass, it's slow enough to push the mass. The causal order might still be the same between Bob and Charlie rather than
Yes, of course. This has to be calculated rigorously through the GR.
So for each inequality, there should be associated limited time.
Absolutely. Yeah. Yeah.
I think we have a question online. Maybe read it out loud.
With the last one. So it says, what is the significance of a superposition of branches with different quantum measurement outcomes being considered indefinitely causally ordered? Did anyone expect it to be impossible? What is the significance of superposition of branches with different quantum measurement outcomes? So, did expect it to be impossible? I don't know if it's impossible, to be honest. Here, I didn't really talk so much about quantum. So actually, there is almost nothing quantum. It's just a sort of a stepping stone to reach something quantum here. So I think the short answer is I have no idea.
Thanks for the very nice talk. It's very deep. Sometimes I think it was even that slide you mentioned something with the quantum four-party switch. So this, can you explain a bit more?
Yeah. No, I was trying to give an example of, so what from the process matrix formal is which objects can violate, right, these inequalities, right? And there is a confusion a little bit with the terminology. This is why I wrote it very explicitly here. So there is a quantum switch, generally, right? There is the unitary quantum switch. That's another thing, right? The unitary quantum switch has four parties. It has a global past, a global future, and the two parties in the middle, right? So for that one, I don't know how much time there is. I'm just going to draw something, perhaps. So you have like, I don't know if you can see, or maybe I can. Okay. Maybe I can write it here. So here, let's say you have, here you have sort of the usual. So the usual quantum switch, what you do is that you output something here such that this gets entangled, the causal order gets entangled, right? But in the unitary case, you have these four parties. I even put the citation here. It's the cyclic quantum causal models, right? And for this, you can choose to play this game between these two parties, the two-cycle game, right? Between, let's say, Alice and Bob. And the thing is that because this party here actually can control whether it will be A and then B, or whether it will be B before A, right? This is controlled by this party here. They can algebraically saturate this inequality, right? So I think what I was trying to say here is just an example of how you can violate this very simple inequality that does that make sense?
Okay, so then this is not the one that we implement in an experiment, right?
No.
It's something else.
No, so the one that is implemented in the experiment is the one that you have traced out this party. You have put the plus state, right, so that you entangle this, and you usually only look at this part. That's why I say the unitary.
Yeah, maybe
yes.
Can discuss because it's very short.
Yeah.
Would also the classical switch.
Yes, exactly. Yeah.
Then thank you.
5-Minuten-Zeichen geben nach 25.
Okidoki. So, warte. Wir haben RQI Circuits, oder? Circuit.
Genau, gibst du zuerst deinen Talk und dann die
Ja,
Presentation.
die brauchen einen Titel, Moment. Jetzt weiß ich nicht. I still need to type my title, sorry.
Die Frage, ja, wir machen Fragen dazwischen und dann die Presentation. Dazu gibt es keine.
Okay. Gut. Was ist es?
Hier.
Hier.
An das Mikrofon.
Mike. Oops.
Ich glaube, allow, weil dann kannst du nicht das hier benutzen.
So I used something from Czaslav's talk because he mentioned sources of gravity in superposition. So I choose this as a title.
Yeah. Our last speaker of the session is Markus Aspelmeyer, and he will tell us more about sources of gravity in superposition.
Thank you very much. Again, following Časlav, and now for something completely different. So we are going to tour the world of experimental physics, and I would like to address the question whether it is feasible to think about sources of gravity in superpositions from an experimental point of view. So can we go beyond thought experiments? The story is well known, so I will, exactly. So, and basically, this is what we are driven by, because the overall opinion over the last 60 years has essentially been that there's no way that we can be pushed by experiments in this field, so we rather be pulled by imagination. So let me pull your imagination and push you towards experiments, okay? So this is now the aim of this talk. So the story is a well-known one. I will do that quickly. It starts with the statement that today all experiments that we have at the interface between quantum physics and gravity can be explained by assuming the validity, number one, of quantum theory, and in combination with the validity of our current theory of gravity, namely GR. So in the best case, the experiments that we have can be described by a quantum field theory in curved spacetime, but that's it. And all those experiments are very beautiful. I don't go into the details now because time is short, but definitely, so what you see here is experiments where the wave packet of a neutron is influenced by Earth's gravitational field in a neutron interferometer. This is the famous Cow experiment by Colella, Oberhauser, and Werner. And here, a gravitational redshift experiment where by raising an apparatus in the lab, an optical clock in that case, you see the frequency of the optical clock shift in Earth's gravitational field. So all of that are beautiful demonstrations how quantum systems are extremely sensitive to classical external gravitational influences. However, the question remains whether we can have phenomena which a classical theory of gravity is unable to explain. This is the question we would like to address. So first answers to that were given back then. This is actually the quote that I had on my title slide. This was also from Feynman at this famous Chapel Hill conference. And the positive answer that was given back at the conference in the discussions was that yes, in principle, if we think of a experiment where we produce one gravitational source mass in a superposition of distinct center of mass states that are in principle distinguishable distinguishable with respect to their gravitational influence. However, in a quantum superposition, then by adding a test mass in the vicinity, we can generate quantum entanglement via this gravitational interaction, which is inconsistent with the very assumption of classical GR, namely that each source mass configuration results in a fixed spacetime geometry within which my test bodies fall along geodesics, and hence I would never be able to generate entanglement. So this is the story. The story essentially concludes with a question that Louis Witten asked, namely also at the conference to Feynman, what prevents this from becoming a practical experiment? And this is what I would like to discuss now. There are essentially two possibilities, two, let's say, special cases of possible experiments that you can perform in order to generate entanglement via gravitational interaction. You could start simply by having two particles into Gaussian quantum states. So as you have two quantum harmonic oscillators separated by a distance d, and just let them interact via a gravitational interaction. Then you have a 1 over r interaction between the two. If you Taylor expand that, the first non-trivial coupling that you get is an XX interaction. So you have two harmonic oscillators coupled via an XX interaction. In quantum optics, we call it a two-mode squeezing operation that generates EPR entanglement between position and momenta of the two particles. So this is one way to do it. The other way to do it is you start with two masses in a superposition of distinct center of mass states that are initially separable. Again, the distance between the two is d, and now you let them interact with each other. What you have then is a variant of the Cow experiment we saw before, namely each mass here evolves in the gravitational potential of the mass there. You get dynamical phases that evolve depending on the position of the other mass here, which eventually results in an entanglement between the two initially separable qubit states, if you want. So from a quantum information perspective, this one realizes a conditional phase gate, and once the phase is -1, you have a control qubit and a target qubit. If they both start out in a superposition, you generate entanglement. Interestingly, even though this seems like two very different experimental situations, if you ask the question, what is the rate at which you generate entanglement through gravitational interactions, where you define delta x in the Gaussian case as the delocalization of your wave packets of the two quantum harmonic oscillator states, and here delta x as the separation of the center of mass states in your non-Gaussian superposition, then it turns out that the rate at which you entangle is essentially the same in those two cases. So, which means now it's rather more a practical question than a dogmatic question, because both approaches yield the same. So now it's up to us to choose what would be the better experimental configuration. Obviously, the challenge now from the experimental point of view is how can you make the rate at which you entangle larger than the coherence rates in your system? Just to give you a feeling for the numbers we are talking about. If I take two atoms, I separate two atoms by a micrometer, let's say. So typical wave packet sizes of atoms is in the order of a few hundred nanometers, then it would take 10 to the 24 seconds for the two atoms to become entangled just via gravitational interaction, assuming that we manage to shield all other non-gravitational forces, which is like 10 to the 6 times larger than the lifetime of our current visible universe. So obviously we need to change something. So well, let's change the mass of the thing. So if we take two lead spheres, approximately 50 micron in size, so there's approximately a Planck mass, there are two Planck mass objects, and we separated them by 100 micron in the center of mass, obviously, because, well, they are 50 microns in size, so this is the minimum separation you can have. Then you see we are down below a second at the time it takes. So this already shows you where to go. What you have to do is you have to take large objects, and you need to make sure that you can prepare large objects in quantum states of motion in order to generate gravitational sources in quantum states. Okay, let's just rewrite this quickly. Instead of the decoherence rate, we now talk about coherence time. It's just 1 over this thing in an experiment. Then we can rewrite this expression into the following condition. So we now have these two masses that we want to entangle via gravitational interaction. D is the distance of this between the center of mass. D naught is the surface distance. I come to that, why this is experimentally important. And then our expression now boils down to this very simple, our condition boils down to this very simple expression, namely that the mass squared, the delocalization square, times the decoherence time, and times 1 over the distance cubed between the two masses needs to be larger than Planck's constant over Newton's constant. If you want to generate entanglement via gravitational interaction, that is the minimum requirement that you have for those approaches. The nice thing about that expression is you can separate it now. You can separate it into a part that you can test in independent quantum experiments. So now, one part in your lab should start building quantum experiments where you maximize mass, delocalization, and the square root of coherence time. Yeah, so the product of that 3 numbers. This is something you have to maximize. And you have to, so you close the door after 10 years, you open it, and the task was maximize this number, and then you need to see where you are. In independent experiments, you need to do gravity tests in which you minimize the distance between two masses such that gravitational interactions are the dominant ones. This is the actual challenge because once you start bringing those two masses together, non-gravitational interactions will start to dominate. So this is the next task. So in the end, you need to do quantum experiments where you maximize mass and delocalization with large coherence time. And you need to do gravity experiments where, using small masses, you minimize the distance in order to maximize the coupling and hence the entanglement rate. Okay? So, here are 3 boundary conditions that you need to consider. And these are more on the experimental side. I apologize for that, but essentially this is sort of, we need to decrease the possible parameter space in which we start designing experiments in. So here's one consideration. This is something that is well known now ever since the big studies and experimental big achievements of the gravitational wave community, namely seismic noise. Seismic noise is something very dramatic. And so the point is everything shakes all the time, okay? And the problem that we have in our experiments is that we have large masses. So think about a harmonically trapped object cooled to the quantum ground state in its trap. So we're talking about a quantum harmonic oscillator, and you ask the question, what is the wave packet size? So my ground state extension of my harmonically trapped particle. You go into an atomic physics lab, you ask the person, oh, you have a rubidium atom trapped. What is the size of your atom? What's the wave packet size? Oh, it's 100 nanometer, because I have a trap frequency of 1 megahertz, I have a mass of 1 atom, and if you then just compute the ground state extension, 100 nanometer. The lab, due to seismic vibrations of this person, actually shakes all the time, okay? It shakes by, let's say, a few picometer. Okay, which is just a fraction of a nanometer. So he doesn't care. So now you try to do the same thing for not 1 atom, but a mass, our 50 micron mass from before, let's say. You have like now 10 to the 10 atoms. And you ask, what is the ground state wave packet size of an object trapped in the same trap, but now with 10 to the 10 atoms, where it's 5 orders of magnitude smaller. So instead of 100 nanometers, suddenly we have a few picometer wave packet size. So if now my lab shakes the same amount, again the few picometer, all hell breaks loose. Because suddenly I see the shaking in my quantum experiment, which I didn't before. So the same amount of shaking actually has a bigger influence when I do a quantum experiment with a more massive particle. So that means I somehow need to take care of that, and I know how my shaking actually decreases with increasing frequency, So the shorter I average in my experiments, the less dramatic is the influence. So what I need to do is I need to confine my duration of the experiment. So what I do is, by principle now, I demand that my experiment does not take longer than 10 milliseconds. This pushes me into a frequency regime where the seismic noise is, well, much less worse than the 1 second regime. Okay, it's still bad, but it's more manageable. So this is number one. So it means now, you see, I confine my coherence time. That's the first condition. So I do a fast experiment. Definitely helps. Second thing is, how do I isolate gravity in my gravity experiments? Because I know there's always non-gravitational forces. If I have two masses and I want them to see interacting via gravity, each and every gravity experiment has Faraday shields. So you have a very well-conducting plate here between the two masses, such that any charge configuration here creates mirror charges, which means that any position-dependent electromagnetic coupling between the two masses is nullified. I generate a coupling now between the shield and the mass, but there's no position dependence anymore. I just generate the so-called DC bias field, electromagnetic one, that I can work with in my experiment, but I don't get any position-dependent coupling between the two masses. So the question is, how well can I do that? And if I look in the literature, the best experiments today, best meaning what is the smallest distance between the two masses that I can achieve and still guarantee experimentally that gravity is the dominating interaction, is 50 micrometer. That's the smallest distance. These were Eric Edelberger's experiment at the University of Washington in Seattle. This is the current world record. So, and what they did was essentially, here for their Faraday shield, they had an aluminum-coated membrane. It was like 10 micron in size. And this served as their shield. What we want to do is we want to push that to 10 micrometer. So we think we are currently collaborating with Eric Edelberger on an experiment where we try to push the distance down to 10 micrometer between the two masses. And we think that this is a number we can work with. We think it's not realistic to go even below, but we will see. Time will tell, but this is now the second assumption that we do. You need a Faraday shield, and you will not be able to go smaller than 10 micron between surfaces. Which brings me to the last condition. This is a decoherence condition. So now we have a Faraday shield, and we have some delocalized particles, some delocalized mass hovering above the Faraday shield. Okay? So the problem is, well, there will be some interaction now. So if there are any losses, if the mirror charges you generate here somehow dissipate, you generate an imprint, you localize essentially your charges, or your charge configuration. So that means you have decoherence. Question is, what should you do about decoherence? Well, so let's say 0th order, you assume, I think it's safe to assume that the decoherence in such a configuration scales somehow to some order with the delocalization over the distance. Well, you can make some dipole arguments and so on, but somehow this is a safe first order assumption. You get decoherence with some order of delta x over d, which now, which means you want to get that number, the ratio between delocalization and distance, very, very small. So you cannot delocalize arbitrarily large and still have small distances. There is a trade-off. Once you fix the distance, there's a maximum delocalization you can afford before decoherence kills you. So that's another constraint now on delta x and d. And you see, the only thing, now we have all three conditions together, the only thing we have not constrained yet is the mass. So we have now put experimental bounds on delta x, on a delocalization, on coherence time, and the distance. If you put all of this together, you get a bound on the mass. Namely, the mass has to be larger than this expression, which is the Planck mass times this parameter here. And this is on the order of 10 to the minus 6, the Planck mass. If the mass is too small, you would have to delocalize too large, and then you would decohere due to the presence of the Faraday shield. And if the mass is too large, well, you can always make the mass large. Yeah? So you get a lower limit on the mass. The mass needs to be at least 10 to the minus 6 times the Planck mass. Planck mass is 10 to the 18 atoms, so you need at least 10 to the 12 atoms in an object in a sort of quantum state of motion delocalized sufficiently. Okay? That is a very firm lower bound. Well, then you just believe me when I say now you basically have to need to take into account all decoherence, sources of decoherence. So you need gas collisions, you need black body radiation, you can go further, you get fluctuations of the trap, you get fluctuations of the trap frequency, the trap position, there might be some residual thermal coupling. So there's a lot of decoherence stuff you eventually will need to take into account, but I can tell you from experience, the most important point, we need to measure these numbers experimentally. So this is actually something that is very important, that we basically determine experimentally what is our noise sources in the experiment, and from that then optimize the rest. So this is my summary from what I have said now. Namely, what I put, remember, this is what we want. We have two masses separated by a surface distance d0 with a Faraday shield. Okay? We want to have a measurement time of our experiment not more than 10 milliseconds. And we want to have a distance, surface distance, on the order of 10 micron. Typical densities of masses that we can assume in the lab is on the order of 10 to the 4 kilogram per cubic meter. This puts us somewhere between dielectrics and superconductors. Okay? So a very dense dielectric has that, a very light superconductor has that. So this is a reasonable density to assume. If I put all of that together now, then I prepared a table here. So what you see is the mass in units of the Planck mass. So if I have, let's say, if I have an object the size of the Planck mass, then I would have to have a delocalization of 1 nanometer, 1.5 nanometer, okay, of the center of mass degree of freedom. With temperatures, environment and particle temperatures on the order of 10 Kelvin in order to get entanglement on a 10 millisecond timescale. Okay? If 80 micrometer is too large for me, this is now an experimental question, can I really quantum control an 80 micrometer mass? Who knows? Well, let's go to 10 to the minus 4 times the Planck mass. I have a 10 to the minus 4 times Planck mass object, then I would have to localize 500 nanometer with, again, temperatures on the order of 10 Kelvin for the particle temperature and the environment temperature. Okay? All of that assumes now that my coherence time is on the order of 10 milliseconds. For a 4 micron object, that means that my pressure that I need, my environment pressure, needs to be on the order of 10 to the minus 15 millibar or so. Which doesn't tell you anything, but it's many orders of magnitude better pressure than we have today in our lab. So right now, the best pressures in the world that exist in 3 laboratories is on the order of 10 to the minus 19 millibar. But that is a huge effort because you have to have cryogenic vacuum chambers and so on and so on. And this is an effort that we will likely have to go, because the larger the mass, the larger is the cross-section for a molecule to hit off from and localize it. So pressure is actually one of our biggest experimental issues. So how much time? We are done, huh? More or less. Okay, so then let me give you 2 quick lab impressions, because now the question is, where are we? Where do we stand? Okay? So I told you we are doing both gravity experiments and quantum experiments. So the gravity experiments that we are doing is essentially Cavendish type experiments. So you have a mass that sits on a pendulum. you bring a second mass very close, and you measure now the rotation of this pendulum here due to gravitational acceleration. Okay, this is data, just raw data from the pendulum without any gravitational interaction, and you see it's very structured. And the reason why this data is very structured is because this pendulum, if you have it here in the lab, sees the traffic light cycle of the road crossing Nussdorfer Straße, Währinger Straße. It sees the fact that there are more people on the street Friday and Saturday nights instead of not on the street the other nights, all that stuff. So basically we see night buses coming and going during the night, all these things. I mean, eventually we managed in our experiment to measure gravity between those two masses. You see the mass is here actually a gold mass, a millimeter in size. So we managed to actually see a gravitational signal. However, for a lab here in the city, this is the smallest you can do. Okay, so this is a 1 millimeter size source mass. Now the next step, what we are doing is we want to go smaller and smaller. So here our next experiment that we're planning is actually have this as the source mass compared to our current mass. So Hans is standing back there. So Hans is building this experiment right now. Actually not in our lab anymore, but here in the tunnel. So we have an underground lab, and this is Hans. And we have an underground lab where we are currently setting up the experiment, and where we basically using masses now of that size. And so the next step in our case right now is to really have measure gravitational fields of a Planck mass object. From the quantum side, what we have been doing is we have started to work on combining solid state devices, solid state because you can cramp a lot of atoms in a small volume, with the ideas of free-falling matter waves. And what we are doing is essentially we take solid objects and trap them in external traps. So for example, in optical traps or magnetic traps. So you can do that in the lab. You can actually take a microscope objective, you can focus light, you can trap a nanoparticle. This is now an object of 10 to the 9 atoms with a radius of 70 nanometers. You can trap that at room temperature, and then you can build a Heisenberg microscope. So basically what that means is you have some complex apparatus where you measure the scattered light that comes back from the object in such a way that the imprecision back action product of your measurement is bounded essentially by Planck's constant, which means that you don't lose any information. The only information loss you have is fundamentally quantum noise, which means you can now use your measurement information. You can use it to reconstruct in real time the phase space of your particle. So basically you can follow the quantum trajectory of the particle at room temperature, and you can even stabilize. So you can feedback cool now, or you can feedback on the particle to stabilize the position in phase space with a precision given by the ground state size. So we can cool now the particle to its quantum ground state of motion in phase space just by looking in it and feeding back the information that we get. And so right now this is really a push button experiment. We push a button and then we get this here, what you see here. This is the ground state. This is the image of a 150 nanometer glass particle in its quantum ground state of motion, sitting at room temperature in our lab in a vacuum chamber. Yeah? So this is what we can do. And now, basically, this is where we are. And now we need to ask the question, okay, so we have a pure state wave packet prepared. This is now our 3 picometer pure state wave packet, okay? And the particle is 150 nanometer. So now the next step is, now we need to expand somehow and maybe even create superposition. So we have that now, pure state wave packet, okay? And question is, can we get something like that? So can we get larger? And this is something we're working on at the moment without going into any details. We came up with a protocol, we call it the Super Mario protocol. So here Mario is the one who built the first generation of the experiment, and now this is the pumped up version in which we think we know how to generate non-Gaussian states. It's a beautiful idea. Essentially, it means we take our wave packet in the harmonic trap, and you switch off the trap, the particle starts to disperse. So you actually delocalize it already. This would maybe already be enough, because now we have a Gaussian delocalization. And then we have an additional interaction here. Essentially, we have a pulse that creates a phase grating and then generates fringes in position and momentum. And basically, you could pick out now two of those fringes then to have a superposition of two center of mass states. If you ask now you should ask the question, okay, what about your parameter space? Okay, so because we had these numbers, you see mass delocalization squared times coherence time, and we need to ask the question, how large is that with respect to h bar over g, assuming that we can have a second particle 10 microns away. Okay, well, the answer is it's 10 to the minus 10. You say, wow, but it's 10 orders of magnitude, it's huge. Oh, this is great. Because this is a 100 nanometer particle, okay? And it's only 5 orders of magnitude, and it's actually mass, 10 orders of magnitude, and it's mass square. So we only need 5 orders of magnitude in mass, okay? Which, if going from a 100 nanometer particle to a 5 micron particle, already does the job, okay? Because, you know, r cubed, so here's the 100 micron particle. This is now the superconducting sphere. We trap a superconducting sphere in a magnetic field, anti-Helmholtz coil configuration. And now what we're trying to do eventually is to now generate quantum states of motion of that superconducting sphere. This would be the next step. Okay, so this would solve the mass problem, and then you would already be in a regime where our wanted parameter is larger than 1. Okay, that's it. So this is where we are at the moment. What we are trying to do right now is we try to address these two questions. How small can we make a gravitational source mass in gravity experiments, and how close can we get? And on the other hand, how massive can we make a quantum system and delocalize it very strongly in order to then eventually combine the two? I need to show that because it's important for just making the point. This is the typical FAQs. What we not learn from observing entanglement generated by gravity. Well, let me just read that. The generation of gravitationally induced entanglement is, number 1, inconsistent with assuming gravity is described by a classical field theory. Does not tell us anything about the quantization of gravity. Is highly likely, this is what we hope, consistent with a low energy linearized quantum field theory of gravity. Excludes by principle all gravitational collapse models. And eventually, this is but more on the side of the Gedanken experiments, if observed together, let's say with initial space-like separation between the two masses, then there are very strong arguments why this requires quantization of gravity in order to avoid any further conflicts. With that, I thank you very much for your attention, and big thanks to my team for making that happen. Thanks.
Thank you very much. It's just a curiosity from a theoretician, just to have orders of magnitude in mind. Every time that probably theoreticians see a metal sphere coming close to the Faraday shield, we think about like Casimir forces, and I don't know, so I have no idea how is the control of the shield itself. But I mean, first, how Casimir forces compared with the gravitational forces at this level, and second, if it's important, wouldn't that actually also generate some kind of entanglement if you allow this? I mean, the shield wouldn't transfer entanglement between the two masses.
So to the first question, this is an unwanted yet wanted side effect of keeping the distances on the level of a few micron. On that level, you can estimate that Casimir forces still do not become dominant. On the question of transfer of entanglement, the main point of the Faraday shield is that through the generation of mirror charge, and it's true for any electromagnetic interaction, you remove the position-dependent coupling to the other side. Of course, you generate all sorts of second order effects, right? I mean, if you would sort of be able to bend the shield, but this is exactly now, this is our duty as thorough experimenters to make sure that that doesn't happen. But I agree, second order effects will definitely be the ones that you have to be careful about. The one with the people?
Yeah, exactly. So it excludes for gravitational collapse models.
Yes.
How about Yoshi's one? Because in Yoshi, what I understand is like it's like a sort of a measurement of the position, and then you do something with the outcome. The measurement can be entangled. So people like combine that you can generate entanglement between the two particles.
So DOC and also the Penrose one, there the decoherence rate scales with the, say, non-overlapping mass distribution. Yeah, so the larger you separate, the larger becomes the decoherence rate. Okay, and the point is that the computation that you do is exactly the same than we do, because what they assume is basically that you have self. So it's the wave packet that interacts on itself. Right? So it's sort of a self-localization of the wave packet. But the point is, you see, since the amount of coupling scales with the distance, and we only start in a situation where the two masses are already separated by 10 microns, the delocalization due to those decoherence models would in principle always be much larger, because they would actually already, in preparing the superposition, they would already predict a rate of decoherence in the preparation that is by definition, because the distance is smaller than the ones that we have, larger than the ones we have. So it has to, for those models that exist, DOC, Penrose and so on, decoherence has, because the distances are always by their assumption smaller than the ones that we have, the decoherence is always larger. So it has to have already decohered by the time we would actually see coherence. Mm-hmm.
Quick question, Markus. So there is an equation that is a bit new to me, which is nice. The fact that you have some lower bound on the mass.
Yes.
And this has an inverse dependence on the coherence. So what's the trade-off there? Because coherence time is also going to depend on the mass, right?
Oh, we fixed the coherence time. Yes, you're right. So the point is, so if the mass, I did not put the area dependence of the mass there. So this assumes that you fix the coherence time to a certain value. And then, but that also means, of course, that you always have to pick then. So basically, when there's a mass dependence, also there will also be an upper bound on the mass. Okay, then the mass will be bounded both from below and from above. Because for 10 millisecond coherence time, I will not be able to do a Planck mass object. Thank you. Yes. Mm-hmm.
Yeah, actually, I think we're running out of time. So let's thank Markus again. He gives an overview over the institute in Vienna of IQOQI.
Very good. So I was asked to give a very brief introduction into essentially job opportunities in, and I take that now a little bit broader, the Vienna research landscape for young RQI entrepreneurs if I may say so in the academic sense. I start first with the IQOQI here, so with the Academy Institute, and then we'll say something more general also. So you are here at one of the institutes of the Austrian Academy of Sciences. The IQOQI Vienna is one of, by now, already 26 research institutes that span the whole range of physical sciences, life sciences, and humanities. And let me just, sorry, I don't know why this doesn't work. Interesting. Okay, no. So basically, well, you have already been guests now at IQOQI for a few days. I hope you're enjoying it. So what we take pride in is that we really have, we think, a unique mix of theory and experiment under one roof, with a very specific focus on foundations of quantum physics, foundations of space-time, matter, and well, everything that comes with it. The institute itself was founded in 2003. We had originally, this was one institute with two locations, in Innsbruck and in Vienna. The founding director here in Vienna was Anton Zeilinger. By now, the two institutes are two separate institutes of the Austrian Academy of Sciences. The building you're in is a historic one. It's an historic site also of the European Physical Society. This was originally founded as the Institut für Radiumforschung, so basic research on the science of radium, which 110 years ago when it was founded, was assumed to be the material and topic of the future. Everything will be driven by radium, and both technology and medicine. And this is why a lot of money back then was invested into this direction. It's like high TC superconductivity in the 1990s, where you saw all the institutes growing. The institute itself consists right now of 8 groups in different domains. We are in total on the order of 60 scientists plus 40 guest researchers. Means we are on the order of 100 people crawling around here at the spaces, both here and at the Faculty of Physics, just over there. We run on third-party grants, and we have a couple of laboratories that are in-house and also external, the one that I showed you, where Hans is doing his experiments at the moment. We have a division in experiments here. This is myself and Anton Zeilinger as group leaders of the institute. And on the theory side, we have Časlav, Markus, and Miguel as group leaders. So all of those positions are actually tenured positions at the Academy of Sciences. Časlav and I are at the same time also scientific directors of the institute, which means that this is sort of the foundations for the direction, scientific direction of the institute. At the same time, we are hosting independent research groups. We always put junior also, such that everyone feels young. And we have currently 3 research groups that are running. Peter Asenbaum's research group on gravitation and quantum physics. He's doing experiment. He just started his group in October. We have the YIRK group with Jelena is remaining. This group is running out next year. And we already have a follow-up group coming. We have Esteban Castorru is joining us. And we have Marius Christodoulou running his group on quantum information structure of spacetime. Now, this is the structure that we have here currently at the IQOQI. Let me tell you a little bit about career opportunities in general, both at the Institute and here in Vienna. So first of all, it's very important to stress, and I think less to the audience here, but hopefully also to the ones who are listening online, that on any level, we are always welcoming applications from both young and experienced researchers all over the world who basically share the enthusiasm that we have doing our work. So I really often get this question, oh, do we have any job openings? I haven't seen anything, so I didn't apply. No, that's not how it works, okay? You just apply. If you think the research that the group is doing is really cool and you would like to contribute, then you just apply, okay? The next thing is if we go directly to master and PhD candidates. So on that level here, there are several ways of getting our attention or getting into the Vienna research landscape. First of all, apply to the group directly. Just write the group leaders and see if they have interest or capacity. Or you can also apply directly to one of the PhD programs that we have for the Vienna research landscape. In particular, we have biannual calls for the Vienna Center for Quantum Science Technology, VCQ. So this is actually our center that has by now collects 20 PIs over 4 institutions in Vienna, foundations, technology-oriented, you name it. Then you can apply to the Vienna Doctoral School of Physics that is hosted by the Faculty of Physics of the university. There's also the Institute of Science Technology Austria that has PhD calls, and this is coming up early next year. We have a new cluster of excellence that is Austria-wide with Austria-wide initiatives and also PhD calls and calls for master students that will open soon. PhD positions are fully funded. We also always, we very often get that question. So basically, do I have to bring my own money when I come as a PhD? No. When you are being made an offer, then you can be sure that the position is paid for and you don't have to work for free. In addition, we also have opportunities for excellence fellowships that always come up situation dependent. Now, on the postdoc level, again, you should contact the groups directly. On top of that, there are also several fellowship opportunities, both on the European and on the national level. On the European level, you may be well aware of the Marie Curie fellowships. On the Austrian level, we do have coming up the Quanta fellowships of our cluster of excellence. This was previously the ESQ postdocs. You will still find that online if you look for that. The FWF, our Austrian funding agency, also has postdoc fellowship possibilities where you can apply together with a group that hosts you then. And if you're interested in coming as a visiting fellow for either a couple of months or just a week, then we have possibilities over our research network Touris on space-time and gravity. Now, the last level of your scientific career, if you are interested in joining us with one of the independent research group. So here's the gist of our approach. So we do host independent research group. I already showed you our current 3 running groups. These groups are limited to 5 years and there's no tenure option. So this is an idea that we adopted following the Max Planck junior groups, where the successful group leaders, after they have interacted with us, actually typically receive position offers that are either tenure track or permanent somewhere, either in Austria or abroad. So this has been a very successful model at Max Planck, and we think that the type of infrastructure and environment, academic environment, that we can provide actually is very well suited for exactly that. Currently, I already showed you, we have 8 groups at the moment. This is what we have in capacity in our building. There is no opening at present, which does not mean, I come back to my point before, that if you're interested, you should not contact us regardless. Then there are other opportunities for independent researchers. You check out the ESC grants, FWF START grants, universities in Vienna, research institutions in Vienna and in Austria are always interested to talk to you when you come with such funding in your bag, because you bring in a lot of money already and resources, and there are situations where you also can negotiate actually relatively attractive packages with the university. Also, just monitor the landscape. Every now and then there is tenure track openings at the different universities here in Vienna, or even just all over the Austrian research landscape. Just to make the point that with respect to promotion of young talent, we do have a successful track record, and these are just a couple of examples over the last 2 years. So here we have 3 examples of group leaders. Markus Huber, who was an independent research group leader at IQOQI, is now a professor at the TU Wien and director of the Atom Institute. Constantino, who was a YIRC group leader at IQOQI, now has a faculty position in Italy. Rupert Ursin was a group leader here at IQOQI on the experimental side. He's now running his own company. Actually, now it's 2 companies. Another example of the group of Miriam. She was a postdoc and then has acquired not only a couple of very successful postdoc fellowships, but now also has managed to get a permanent group leader position at the University of Geneva. Other example from Huber, what?
No, it's group leader in Geneva, permanent.
Sorry, group leader.
She just became permanent in Paris.
Oh, okay, very nice. So even better. So I was half right and not wrong. Another example here, Hayata from Markus Huber's group has now become assistant professor in Tokyo. And in total, also within the last 2 years, 8 of our postdocs at IQOQI have acquired prestigious fellowships, both national ones and EU ones. So I think with that, I hope it's clear that here the research landscape at IQOQI in Vienna is very promising. It's a good place to be from the master level up to the group leader level. We think we have many nice examples where we have acted as a nucleus for new publication-wise, scientific achievement-wise, and we actually hope that this will continue in the future. So I essentially will stop with that. If you have any further questions, again, please just write to the group leaders themselves, get in touch, ask Časlav, because I have to teach now. And very good. Okay, thanks a lot.
Thank you very much, Markus. And with no further ado, we open the coffee break and we will continue on time, so in half an hour at 3:30.
right, welcome back everybody. I hope you enjoyed your coffee break. We start the second session of the conference today, and the first speaker is going to be Markus Müller.
Okay, thanks for the introduction. Can you hear me? Does that work? Yes, great. Okay. Well, so thanks everyone for staying so long on a Friday afternoon and for having me, and Ann-Kathrin and all others, thanks for the organization. I'm here to give a brief overview essentially on what our group has been doing in the last few years, maybe the last few months as well. So this is a picture of us at the moment. So there's Caroline and Stefan, who is also here and will speak after my talk, and Thomas and Albert. Also Andy contributed a lot over the last few years and was part of our group. Okay, so what are we going to talk about? So certainly we have a lot of topics that we work on. For example, quantum thermodynamics, philosophy of physics, several other topics that I'm not going to talk about today. But since it's about relativistic quantum information, I'll talk about these topics here. So the first part will really to just say very briefly what we've been doing in the context of quantum reference frames. Now this will be very brief, so most of you know what this is, and you've already heard a talk by Časlav and several other people about this. So really keep this in the as a kind of a teaser. So just an overview, what have we looked at, what might be interesting questions perhaps also to tackle in the future. The second part, okay, the first part is maybe over the last 2 or 3 years mostly. The second part motivates a bit the research program that we've been pursuing, which is to understand the relation between quantum theory as an abstract Hilbert space theory of probabilities and spacetime and how the two interact. The second part is actually older already. It's 9 years old, so I apologize to those of you who've already heard it. But I think it's a nice thought experiment that somewhat motivates the research. The third part, however, is pretty young. It's -1 month young. So it will appear in the archive towards the end of the month. So everybody who wants to now steal the results I'm talking about, you have like 3 weeks to write it up and submit. Okay, yes, so it will be about spin-bounded correlation and something that we might call metrological games somehow. But you'll see what I'm talking about. So quantum reference frames. Here's a picture that most of you have seen. This is by one of the first papers on this topic by Flaminia, Esteban, and Časlav, where you say, in a very simple experiment here, or thought experiment, say you have 3 particles and you have translation invariance, and you can choose your coordinate system as you wish. Then maybe what you want to do is you say, oh, I start with a state like the above, and I do a quantum reference frame transformation and I go to the state below. So above you would say, well, there's an origin of my coordinate system and particle C happens to sit at the origin. Particle A is a superposition of 2 positions. Particle B is like a wave packet sitting further away. Perhaps it's something like, no, it doesn't react. Let's see. Okay, here you go. So maybe it's a state like the above, right? So, and then you say, what if I jump into the perspective of particle A? So you move your coordinate system so that particle A arrives at the origin. The idea is you do this branch by branch in a coherent way. So what you end up is like a big superposition state where A factors out, A becomes the 0. But now, depending on whether A was to the left or to the right, whether it's this or that branch, you'll have the CB arrangement like collectively be to the left or being to the right. So you end up with a state that's an entangled state between C and B. Whereas previously it was a product state. Now, suppose, however, that you believe that physics is invariant in some sense under quantum reference frame transformations. So all the essential things you describe in one frame remain in the other frame. And also think, for example, that this particle B is really very far away. Perhaps it has been prepared in another galaxy or so, like really independently from C and A. Then how then can it be that this is reference frame dependent? In other words, how can the question of whether B is in a product state with AC be quantum reference frame dependent? So has it been independently prepared or not? How do you understand this? In other words, this asks somehow for the interplay of the compositional structure and the quantum reference frame symmetries that you believe that you have. So we've addressed this in a paper here. That's with Marius Krum, also was in our group, and Philipp Höhn. So basically we ask, how do we compose systems if we bring in an independent system in a way that is reference frame and quantum reference frame independent, right? It's basically the tensor product rule is not the right thing anymore. You need to talk about what observables are accessible to which observer, right? The dual question is like not what you bring in a system, but if you trace out a system. Right? So you say if I forget the third particle, for example, this one doesn't work really anymore. Okay. So if I forget the third particle and I think of tracing it out, then this phase theta that you see on top here, you would get, here you would think that if you have only access to system A and perhaps system C, then you can measure theta. But here it seems like if you have access to A and C only, then you cannot measure theta because the partial trace will kill it. And this is a paradox that has first been raised in an apparent paradox in this paper by Angelo, Popescu, Brunner, and co-authors. And what we do is we essentially analyze this question. We give an answer to that question. The answer is basically you have to operationalize what you mean by bringing in another particle. You have to replace the tensor product by saying how you embed fewer into more particles, how the algebras are embedded. And if you do it in, let's say, most symmetric way, the most symmetric choice gives you what we call the relational trace. It's like a replacement of the partial trace. And if you apply it, you will see that indeed you still have access to the phase theta on the first two particles if you forget the third particle. Right. Now to do so, I should say that what we did is like usually think of the real line as a continuous line where you have a continuous transformation group acting. We found it convenient to just model it in a discrete way. So you discretize the line and glue it together. This gives you a finite dimensional Hilbert space, and then you can work out everything explicitly in finite dimensions. Their position and momentum eigenstates, and you can just work it out all out explicitly with quantum information tools. And so this is also described in this other paper that we've written there. Yeah, this is very interesting for you start that you want to read up something new and don't want to bother with technicalities, and this might be perhaps nice to look at. Right, so in addition to this way of describing quantum reference frames, there's kind of a different way of talking about quantum reference frames, which is sometimes called the perspective neutral framework. Again, several people have been involved in this. Philip Höhn was the main proponent of this. The idea is essentially, it's a bit like the Page-Wouters mechanism. So you start with a globally symmetric quantum state subject to a constraint, and then you can jump into the different perspectives of the different subsystems. And what we did, and this is now also in collaboration with Anne-Catherine de la Hamette from Czaslav's group, who's also here, we generalized this approach to basically arbitrary groups, unimodular groups, and analyzed it a bit further. Right. Also, this is, I think, kind of, you can have a nice picture here. This is something we looked at, again, with Anne-Catherine, and now Stefan is also on this paper, where we ask, what actually is a good or a bad quantum reference frame? Right. And think of, for concreteness, so what some of you may know is the Page-Wouters mechanism. In the Page-Wouters mechanism, you say you have a system S and you have a reference. The reference is typically thought of as a clock, so a system and a clock. And you say, like, I have a global state, and this global state is time translation invariant. So it's annihilated by the total Hamiltonian. So nothing moves, it's frozen in time, that's the idea. But now if you measure the clock system and you find some time t, then you get a conditional state on your system that does depend on the time and still satisfies actually the Schrödinger equation. Now if you look at this construction, you will not only see that this global state is time translation invariant, but certainly when you look at what it looks like, then it's very massively entangled. And so you'd guess that it's this entanglement somehow that correlates the clock and the system, and that is responsible for the kind of time translation asymmetry that you get after you measured the clock. And what we did was to make this rigorous and quantitative, and not only for time translations, but for arbitrary groups. So it turns out that somehow the more entangled the global state is, your global invariant state, the more asymmetric is the conditional state on your system. So think of this picture here. You have a global state on RS that's entangled. If it's very strongly entangled and you measure the reference, you look at the conditional state of the system, then the resulting state will be very asymmetric. So if your symmetry is the rotations around the circle, then this will be very much different from its rotated version. But if you don't have that much entanglement, then you have a stronger overlap between the state and its translated version, right? So this gives the idea that somehow entanglement, time comes from entanglement, a kind of quantitative version that you formulate here in terms of the Rényi 2 entanglement entropy versus some sort of asymmetry measure that we have. Okay, should probably go on a bit. Right, so you can do a couple more things here. Average over the Hilbert space to get a quantity that tells you how good is your reference frame actually in a state-independent way, and a couple of other things that we've looked at here. Good. Now, the other topic that we've been interested in is the relation between space-time and quantum theory. And here's a thought experiment that some of you have already seen, I'm sure, that has to do with the relativity of simultaneity and the quantum bit. So in a quantum bit, we typically think of like the qubit Bloch ball. That's the quantum bit in standard complex quantum theory. But nature wouldn't have to be that way. So there is even work by Jordan, von Neumann, and Wigner on generalizations of the quantum formalism, where they essentially say, well, you could have different sorts of operator algebras, which describe physics, needn't be the complex matrices, but it could be operator algebras that give you bits that look differently. For example, your bit could be a classical bit. And the qubit Bloch ball is a 3 ball, but the classical bit would be something like a 1-dimensional ball. We have like 0 and 1 and all the statistical mixtures. If you had quantum theory over the real numbers, you would basically get only the equatorial plane of the qubit, which is a circle. But you could have higher dimensional balls that describe bits. If you think of quantum theory over the quaternions, which you can write down and hypothesize what that would work like in physics, you would get a 5-dimensional ball, for example. Now, right, so Q-trit, for example, in contrast, would not be a ball, but some more complex shape of density matrices. Now, the idea is like, why do we have dimension 3, right? So certainly you can ask because we have complex quantum theory, right? But maybe there's a more principled approach. And so you can ask, maybe space-time has also something to do with this 3-dimensionality of the Bloch ball. And here's one thought experiment where you can make that somewhat rigorous, which is with Andy Garner and then Oscar Dalston a couple of years ago already. So you think of a Mach 10 interferometer, where you think of a particle that can travel either lower or the upper branch. And the which path information, where it sits, is described by a bit. It's a binary alternative. For the state space, it looks like a Bloch sphere. So if it's the north pole state of the Bloch sphere, that would mean that the particle is definitely in the upper branch. South pole state would mean it's definitely in the lower branch. If it's a state somewhere on the equator, then you would say, well, it's like 50-50. So if you measure, you would find 50-50 probability of being up or down. If this is a standard qubit, you can all check that this is the case. But it works for d-dimensional Bloch balls as well. So in general, you'd say the probability of finding the particle in the upper branch has to do with this z coordinate here. It must be linear in this coordinate, so it's something like 1/2 z plus 1. Now you can ask, well, what if I have Alice and Bob now? So 2 physicists that sit here close to the arms, and they can do something. So maybe they can insert a little piece of glass or something to the arms. What's it that they can do? Assume they're interested only in stuff that's reversible, so that doesn't lead to information loss. Well, in a way, it's quite clear that this must be a transformation that takes your state and maps it to another state, and you can undo it, so it must rotate the Bloch ball somehow. And it also cannot move the particle from here to there. Since it's done locally in one of the arms, it must preserve the probability that the particle sits here. It's like no signaling. But this means that it must preserve the z-axis of your Bloch ball, because that's what the probability is, essentially. Bob can do the same on the other branch, right? Same constraints of what that does to the Bloch ball. And well, in the most general case, you would say there are no other constraints. All rotations that preserve this axis, and this is like all the rotations in dimension d minus 1. You lose 1 dimension because you fix this axis. Good. Now you enter your favorite spaceship and fly by, right? And look at the setup. And then you say, oh, interesting. This is a scenario where first Alice chooses her transformation and then does Bob. But then your friend flies by in a spaceship and certainly sees these space-like separated events to happen in the other order. So Bob does first his transformation and then Alice. And for that, to not change the physics means not changing the outcome probabilities of your final detector clicks, which means that these transformations must commute, whatever they do. So for all transformations in SOD-1. Now we all know that rotations commute in the plane in 2 dimensions, but not in higher dimensions. So in order to have that, you need to have that the dimension of the Bloch ball is at most 3. Right. And indeed it is 3, as we think we have from our standard description. Now you can tweak it a little bit. You can say, well, so far essentially what I assumed is that everything that Alice can do, Bob can also do. In particular, whatever Alice can do, Bob can undo that, right? Put a piece of glass, Bob puts the same piece of glass, nothing happens. What if I just assume that whatever they can do is isomorphic? Like there's a class of pieces of glass that Alice can do and like isomorphic pieces of glass that Bob can do, but they don't talk to each other perhaps. So the groups are not identical but isomorphic, and then you see that D equal to 5 is also a possibility, and that was exactly quaternionic quantum mechanics. So you can come up with a theorem where you say here are 3 assumptions. One is that the beam splitter can prepare any of these probabilities to be up or down. The second, if you have 2 pure states with the same probability, you can always move from one to the other just by local operations. And then you say whatever A and B can do are isomorphic. So the second somehow says, for example, that you don't have any degrees of freedoms of the ball sitting here without talking to you. That could always be a 7 ball and 4 of the degrees of freedom do nothing. So you exclude this here. Turns out that this still allows every dimension, but now you assume relativity of simultaneity, and then you get only the cases 1, 2, 3, and 5, right, as the Bloch ball dimensions. Let me not read this, but just the conclusion is that relativity of simultaneity singles out the associative division algebras from these infinitely many possible state spaces. And this is somewhat suggestive. You see that somehow in order for a probabilistic theory to talk to space-time in a way that we wanted to have some certain simple properties to hold, this can be very constraining. Now what can we do with this? So this is now a recent project in the last part that I talk about with all my group that I've been working on like the last year or so, which is on kind of spin-bounded correlations. So this is the idea. So somehow, there are other arguments too that say that somehow quantum theory seems to be tailor-made to fit into space and time in a way that no other probabilistic theory fits. Can we show or analyze this more explicitly? And one way to do it is to look at metrological games or metrological scenarios and ask whether quantum theory is optimal for games that you can play in this context. So here's a scenario where the goal is somehow you have a rotation that's performed, maybe a referee performs that rotation to your system by an angle alpha around a fixed axis. And you want to learn something about alpha by measuring the system that senses it. Right? So if you think of like a preparation device, like a single photon source, and you rotate it, the statistics will change. You can learn something about the angle and the change of statistics. Or maybe your particle passes this region. It senses what's going on here, like in metrology, and then you want to do a measurement and estimate some parameter. Good. Certainly, if you send a classical gyroscope, then this is trivial. You can just read off the angle. Right? So it becomes interesting. The system is small in some sense. Right? So to make it interesting, let's make an assumption about how small the system is and how well it responds to rotations. Let's assume that its spin is bounded. For example, it's a particle at most spin j. A classical physics system like a gyroscope would correspond to a j equal to infinity system. That would then allow you to read off the angle exactly, but what if the angle is small? Also, let's suppose we're asking only binary questions, like yes-no questions. So your outcome is always -1 or +1. So you can say, well, if I assume that quantum theory holds, then this gives me a bunch of correlations or probabilities that are consistent with spin J quantum theory, and I call them quantum spin J correlations. You say, well, what is that? Well, I have a probability of getting +1 or probably of outcome B, given that I had rotation angle alpha, which is given by the Born rule, right? So what's the Born rule? You have your measurement operators that tell you what the measurement is. You have your initial state, and the rotation acts now on the state, right? So what is this? Where the rotations act on the state, we are unitaries. You have a unitary representation of the rotation group. It's not SO3, it's SO2, so it's actually a bit simpler. But you would say if the spin is at most J, then you can write it in that form. You can basically diagonalize it, and you get a bunch of complex exponentials. And whatever appears in the exponent is the factor is at most J, right? Think of just ordinary SU2, but fixed to the Z-axis, and they look like this, the transformations that you get. Consequence, for example, is that your probability rule that you have is always a bunch of sines and cosines. Yeah? It's a trigonometric polynomial of degree at most 2J. So if you spin 1/2 particle, then you might perhaps get dependence of outcome plus on the angle, like 1/2 plus 1/2 cosine alpha or things like this. And you find lots of these equations when you look at actual experiments. This is kind of very realistic in a way, when people rotate the polarizers in the Bell experiment and so on. Good. Now, what is a more general spin J correlation? Well, the idea is we just we take the probability rules and the fact that they are trigonometric polynomials of degree 2J, but we forget that they should come from the Born rule. Let's not assume this. Let's just say, well, these kind of quantum rotation boxes, now we have general rotation boxes, and these are probability rules. Everything's probabilities between 0 and 1, but not from the Born rule. And you can show indeed that this can come just from representations acting on arbitrary state spaces, which are not quantum necessarily. Then you can get all of these as your probability rules, how your physical system could react. Good, so we can take them side by side, and certainly quantum ones are inside the more general rotation box correlations. In our paper now that's upcoming, we show that certainly for spin 0 means it depends not on the angle, not at all. Yeah. These sets are the same. For spin 1/2, they are also the same, which is kind of easy to show. And for spin 1, they also agree. But this is very difficult to show, in fact. So for spins 0, 1/2, and 1, quantum theory gives you already the most general correlations and is therefore optimal for all these metrological tasks. But not for spin 3/2 and higher. Yeah. It's interesting, because we think like, oh, the elementary particles that we know of all have spin 0, 1/2, and 1. But suppose, what about spin 3/2? So here's something you can do. Here's a game that you can play. Yeah. It's not the most natural game, but something you can play. You know? So some referee draws an angle alpha between 0 and 2 pi at random. Not uniformly, but with a certain probability density, which looks like this, and it's plotted here. That's the probability density. Yeah, well. And the goal is not to determine what the angle was, but whether it has been chosen from the red region or from the blue region. Okay. Essentially, red and blue mean where these cosine and sine terms are either positive or negative. Yeah. Turns out that when you have quantum spin 3/2 systems, then they allow you to win this game with a probability of like 85%. But if you have more general spin 3/2 systems, they would allow you to win this with a probability of about 88%. Okay. Yeah. So I mean, this tells you on the one hand that quantum 3/2 spin set is a strict subset of the more general one. Also, you can say that this more general set is actually an outer SDP, semi-definite programming approximation to the quantum set. And so it allows you to get computationally efficient bounds on how a quantum system could behave. Here's where it comes from. So these probabilities all have this form with a bunch of sines and cosines. Turns out that if it's a quantum box, then these two coefficients, C2 and S3, their sum is always less than or equal to 1 over square root of 3. It's like a kind of Zittelson type bound. But you can write down an example polynomial that's also of that degree and that is between 0 and 1, and that violates it because it gives you a higher value. Okay, I'm running out of time anyway, so let me stop here. So this is what I've shown you, a bunch of stuff on quantum reference frames and dimensionality of the qubit. I've shown you that quantum theory is optimal in metrological games for spins 0, 1/2, and 1, but not for 3/2 and higher. Now let me just finally mention the motivation for doing this. So why are we interested in this? Well, one motivation is indeed, and Stefan will talk about this in the next talk, that you can use some of this to come up with new semi-device independent protocols, for example, to generate random numbers. Because instead of assuming a dimensionality of a quantum system, you can perhaps assume something about the spin, which is maybe physically more motivated. For me, the main motivation is really foundational, and perhaps to make a very small and modest step or collect a few modest insights for quantum gravity, which is all about the interplay of quantum theory and space-time physics. So how do the structures play together of these two parts of physics, of probabilities and space-time? Also, you can say this is something like studying correlations that are resource-bounded. And the paradigmatic example that you typically look at would be quantum speed limits, where you bound the energy and say how quickly can a state evolve to an orthogonal state. And this is kind of a more general view where I study correlations with respect to physical resource bounds. There's also some nice mathematical physics for those of you who like this. It's related to orbitopes, SDPs, and harmonic analysis, and so on. Good, so here are the papers on the archive if you're interested. And yeah, I'll stop here. Thanks.
Thank you, Markus. We have time for a couple of questions.
Regarding the dimensionality of the qubit from the second section, I was wondering if this relativity of simultaneity constrains the dimensionality of the space that can be also isomorphic to the number system. For example, is it like, does it constrain R2 or C? Do you know what I mean?
Oh, R2, you mean the real to the second power?
Yes, exactly.
So I mean, in a way you can here, so when you have that result in the end, you don't need to talk about number fields, no? If you want, you can just say, oh, this is a D ball, right? What can I say about the dimension D? Yes. Right? It just so happens that you can interpret them as qubits over these fields. Right? And perhaps, I mean, one thing you might think is, well, you know, if I tensor things like independently, then I have to multiply elements of this field, like real times real, complex times complex, quaternionic times quaternionic is then perhaps, you know, or if it's octonionic that I get in trouble and then this violates somehow no signaling or so. But this intuition doesn't quite hold up because you're not really talking about composition in this sense, in the sense of the tensor product. It's like a more bare-boned sense of like being either here or there as a two-level system. And so this reasoning would not directly work.
Okay. So in this case, like, I think you already write, sorry.
No, it's fine.
Okay, to continue? Okay, sorry. Like SO4 is, either SO4 or SU2, which are, they both included, right? So.
Yeah, so here what this groups mean is that, so GAB is what can A and B do locally and what group can they generate of the local pieces of glass, if you want. Turns out to be SO4, like all the rotations of the 5-ball that fixes this one axis. Now what can A do locally? It's basically, SU2, and B can also do, so locally some kind of SU2. There's kind of group theory, how they sit inside the SO4. It's kind of an interesting group theory, a special case. That's why D equal to 5 survives here. Yeah.
Yeah, about this, if you, I mean, you got to restrict a lot the possible dimensions just by considering the most simple, right, quantum system. Does it exhaust all? I mean, it's not possible to restrict even more, or maybe if I could consider just as like a simple example, something which divides in 3. I don't know if that's and wouldn't that restrict any even more, or you're analyzing, and that's actually the restriction that comes from one qubit is actually it's all that can be done?
So far, we haven't really generalized this. So the problem, even when you go to 3 branches, is like you don't have an infinite sequence of natural 3-level systems. Yeah? So these d-dimensional balls is like an infinite sequence of bits, and you can kill most of them, and then you're happy. But already for trits, so in this context, you only have the real, the complex, the quaternionic, and the octonionic one, and then that's it. And probably you can sit down and run the argument and kill the octonionic case. I'm not sure if that's worth it. Yeah, but
so the only case where you have this nice interpretation for this space of pure states is basically the qubit or products of that. So there's no other systems, no other system in which the space of pure states cannot is some other space which is not either the boundary of the Blois sphere and products of that.
It could be. Yeah? You could play this game. Say, here's a class of state spaces, possible ones, shapes, if you want, with n outcomes. Which one of them? Let's work out which of them fit somehow on an n-arm interferometer with and respect relativity of simultaneity. We just haven't done it, right? But you could do it, right? And see what kind of constraints this gives you. But in the end, we drifted more in that direction where we don't want to assume full state space and rule them out, but really more in this device-independent black box picture about what about the statistics that you see in an experiment. We found this in the end somehow more like clearer about what the phenomenology would be in the end.
In the interest of time, thank you, Markus.
Thanks. Thank you. Yep.
Yeah, thank you. So today I'm going to talk about one of our papers called Theory-Independent Randomness Generation from Space-Time Symmetries, which is joint work with Caroline Jones, Apadula, and Markus Müller. All of this is part of a broader research project, which already Markus mentioned in his last talk, where we try to build a framework where we can study the interplay of space-time geometry and the probabilities of events. We do this by extracting symmetries from the geometry of space-time, and then via group representation theory, we see what this implies for semi-device independent scenarios. Or we frame it in a more clickbait way. We put back the black box approach of quantum information into space and time. So this is what I'm going to talk about today. First, I will give you a short introduction into the semi-device independent framework. Then I will explain the exact setup of our random number generator, tell you a bit what was already done in the literature. Then I will tell you what we have done, present you our results first assuming quantum theory and then going beyond quantum theory. And yeah, finally I will give you a conclusion and an outlook what we will do next. So before we go to the semi-device independent approach, I will talk a bit about the device independent approach, which probably most of you have seen. It's just a bell setup. I will not go into many details because I think you're all pretty familiar. But what I want to point out here is that basically in this setup, we do not assume anything about the boxes. We only know to take inputs and create outputs, but we don't assume how the inner working is, like from which theory we assume in the first place. All we do is we study the probability distributions that we get in the end. And then we can try to see if specific correlations are compatible with specific theories. For example, like this, I think also everybody has seen this, which, like, if you have some correlations that are within this set, then we know there can be some classical mechanism inside the box that explains them. If you're in the blue area, then there's some quantum description, and like the most general ones are just non-signaling descriptions where, like, we only assume that you don't have any signaling between those two boxes. Okay, so this is very nice. We learn a lot about nature, but it's very hard to implement in the laboratory. It has been done, but it's very hard. So what people also are interested in are semi-device independent scenarios where we actually give up this restriction, this assumption that the two boxes are space-like separated, and we actually allow communication between those two boxes. And we will especially look at a specific scenario where Alice, the first box, can signal something to Bob. But if we don't make any further assumptions here, then basically we can create any kind of probability distributions that we want, even within classical probability theory. So that's exactly the reason why we go from the completely device-independent setup to some semi-device setup where we will describe at least some parts, a bit more of our setup, and make some assumptions about them. So the first one is that we assume that basically all of this can be described by quantum mechanics, and the transmitted system is a quantum system. And now we can make assumptions about the transmitted systems. For example, we could say, okay, we bound the dimension of the Hilbert space. For example, we could say the transmitted system is always a qubit. This is also very hard to certify in the laboratory. So people thought about what could we do else. So what they did, especially in the von Himbeek paper here, is they said, okay, we have an additional observable, for example, the energy, and we bound this observable. So we say the transmitted system, the expectation value for the energy must be bounded, and then you can basically analyze the setup, and you will see that you can actually create randomness with the setup. The only problem with this is that this still relies on the validity of quantum mechanics. So here we assume that our measurements are POVMs, our system is really described by quantum state, and this is something where we want to be more general. We don't want to make these assumptions, but still want to certify randomness. So what we did, we looked at the following setup, which was also introduced by Markus, where you have two boxes, and basically you can rotate the first box. And you have two different settings. So the first one is either you do nothing to the box, or you rotate it by a given angle alpha, which is arbitrary but fixed. And then we will make some assumptions on the system that is transmitted. So we say it has to be in some statistical response to our space-time symmetry, in our case to the rotations. And we will basically make a bound on how this can behave under this rotation. And then we only consider here two output measurements. So first we will describe this within quantum mechanics, a bit as a warm-up and also to understand what's going on. And we'll define the set of all the correlations that we can find within the setup, where we have the two correlators, E of x, which is basically just the expectation value of some observable with two outputs, either plus or minus 1. So you could also read this as the probability of finding plus minus the probability of minus given for a setting x. And the states that will be sent depends on your input. So either if you input 1, then when you do nothing to the box, you will send phi 1. And if you rotate the first box, you send phi 2, and this is connected with this representation of SO2. And yeah, so this is also where our rotation comes in, and we can actually implement our assumption on the bound of, so we can bound the spin on this. So here we can say, okay, like our representation is of this form, and it's bounded up and below with some j, which is either an integer or a half integer. Yeah, so this would be just how the state would transform then. What is important here is, since we make this assumption on this upper bound, the state cannot be just like jump into an orthogonal state. So basically what you have here, phi1 and phi2 have to have some overlap. So they're not perfectly indistinguishable as long as j alpha is smaller than pi over 2. And this is basically the case that we will look at because this one is boring. There you have two distinguishable states, perfectly distinguishable states, and you could do whatever you want with that. So this parameter gamma here can be now used to give you the shape of the set up here. There are some results in the literature, and we use them, and then you can basically derive this form here, which tells you exactly that this is the shape of the quantum set. Yeah, good. To talk about randomness certification, we also have to know what are the classical probabilities that you can see. And basically, this is when our box either behaves in a deterministic way, or if we have convex combinations of so classical probability distribution over deterministic behaviors of those boxes, which will adjust this line here. And if you look at the definition, what I want to stress here is that the definition still depends on our definition of the quantum boxes, which is in the first place not a really good thing to do, but I will argue later that this doesn't actually matter, and we don't have to worry about it. Okay, so yeah, so far we only talked about pure states. In principle, we could define a similar set just using mixed states. As it turns out, like, we don't care if we work with pure mixed states, because obviously the set of pure states is a subset of the mixed states, but also the other way around is true. We can use some purification argument where we purify in a way that we don't pick up any additional spin, and therefore we see this is also a subset, and therefore both of the correlation sets are the same. Yeah. And what we also did is we looked at this set here, which we called the relaxed quantum set, where we wanted to grant some room for experimental errors. Maybe this form is not very enlightening, but you can actually rewrite all of this in this form. And this has a nice interpretation. Basically, what we are saying is we trust, for example, with a probability of 90% that our assumption holds, like our bound of the spin. And in 10% of the cases, we don't know. So it could be any kind of correlations. Yeah, and then basically what this does to your set, it just broadens it a bit. So yeah. Yeah, one example that we had in mind is for coherent states, where basically the particle number is connected to the spin, and then you can actually determine this this delta explicitly. Yeah, the details are not very important here. Yeah, you could also do the same thing for the classical set. So again, we are now sure with, for example, 90% that our assumption holds. With 10%, we don't know what is happening. So yeah, we just can have any kind of correlations. And this will give us the full picture here. Using this, we can now talk about randomness certification. So we are describing a random number generator. So we actually want to know that we're actually getting some random numbers. And therefore, we will analyze this quantity here, this entropy. And basically, what is important here, it is a conditional entropy, and it is also conditioned on your hidden variables. So this means it's also random to some eavesdropper who might have more classical knowledge about the setup and the inner workings of the boxes that we don't have. And yeah, basically, you then want to lower bound this entropy and find the lower bound of this. Details, again, are not super important as here. But what is important is basically when this is greater than 0, then you have some certified randomness. And this is equivalent of being outside of the classical set. So when you're somewhere here in this area, then you know that basically you have some random numbers which are also random to some eavesdropper. Okay, so also all of this so far heavily relied on quantum mechanics, and that quantum mechanics is true. So what we now want to do is we want to drop quantum theory and describe all of this in a more theory-independent way. And as also Markus explained before, what we can basically do is we can look at these probability distributions, which we can just write as a Fourier series, since we assume that they are 2π periodic, and implement our assumption here by saying that our series has to terminate at 2j. This is actually corresponding to the same assumption as we had before. The factor 2j comes because we are looking at the probability distributions and not the representation on the Hilbert space. But it would in the quantum case, this would lead to the same bound here. There are different ways to derive this. The first one was either just looking at this 2π periodicity, using that you can develop this into a Fourier series. But there's also another way of arguing, which is more general. So this would also work for other groups, that you say, okay, actually this form of probability distribution comes from some underlying representation on some state space, which is not necessarily a quantum state space. And you could use this theorem to derive the same form. Good. So then again, we will define now the rotational box set, the correlations from the rotational boxes in a very similar way as before. So you have those two correlators. We just assume now that the probabilities, how they are created, are of this form here. And then we again give a description of the set in a different way. For this we use this lemma, which is in general true for trigonometrical polynomials of degree n. N is in our case 2j. And then with some calculations, you actually found the same inequality as before, which means for 2 inputs and 2 outputs, the 2 sets are the same. So the quantum set of the correlations from quantum mechanics are the same as for the rotational boxes. Which is a nice result, because this basically also certifies that now the randomness generation is also valid even if quantum mechanics doesn't hold. So we could redefine the classical sets now using basically these the correlations from this set here. So in upcoming work, Markus already talked about this. We are now studying not only 2 input to output setting, but also continuous inputs, where we basically look at the set of space-time boxes and the set of quantum boxes, and we study those kind of probability distributions, either just saying, okay, they're of this general form, or if they have, or for the quantum case, they have to come from the Born rule. And as Markus also mentioned, it's pretty trivial that basically the quantum set must be a subset of the rotational box set. But the other way around, and this is also worked together with Thomas Galley, we found that for the case the j is 0, 1/2, and 1, they're still the same. But if you go to 3/2 or larger j, then there is a difference and there is a gap. So the conclusion of my talk is basically that, as we've seen in this 2 input to output setting, the set of correlations that come from the rotational boxes are exactly the same as for the quantum case, which implies that also the randomness generation of is also secure against post-quantum eavesdroppers. And for continuous inputs, we will see a gap, which we can try to then study the underlying GPTs and see which implications that has. So as a further outlook, we try to analyze different symmetry groups and also some other setups and other scenarios. And something that is very closely related to our setup described here are also speed limits, which would go beyond quantum theory. So yeah.
Thank you so much. Are there any questions? It's a very clear talk.
Before, when you did like semi-bias independent scenario, and you had like some concerns about assuming the dimension of the system.
Yeah.
But we don't have the same concerns about assuming what is the spin of the system.
I mean, maybe for the spin, that's more concerning. I mean, here it's also, we could also see it as a time model, but I think where it's easier to certify this is, for example, for the energy. Then you would just replace your SO2 symmetry with a translation symmetry, and there it's easier to certify. Just look at your energy bill. If it's not infinitely high or something, you could give some bound on that. Especially if you say, okay, we grant some room for error. Just saying, okay, we know in 90% of the cases it's like the assumption holds. But yeah.
Nobody online? Well, in that case, let's thank again Stefan.
Or do you prefer the 10-minute warning so that you have 5-minute warning? I'm going to be running over time anyway.
Okay, right.
We are even running early though.
We have lots of time.
So we're not 7 minutes ahead of schedule.
Yeah.
Good.
Don't stress. Okay. Should work.
All right, so next up we have Markus Christodoulou.
All right. So I was asked for this talk to give a high-level presentation of what we do in my group, which I took to mean that I will just have drawings, mainly, in the talk. And I will cite nobody also except my papers, the ones from the past year in particular. So there is almost no context. And about the group, it's pretty new. It's 1 year now. Ofek is second year PhD, and Sarah is finishing her master's. Andrea is about 1 year and a half here now as a postdoc, and Maria just arrived last week. I'm very, very happy about it. It's been a challenge starting a new group. It's a big step. And the principle I followed in forming the group was to hire people that are smarter than me, which is great because then they're very good. Downside is that I feel stupid sometimes. But I'm trying to deal with that. And the maxims that I follow are pretty much these quotes that quantum mechanics is meant to be counterintuitive, if you want, and that we don't really know what we're doing. And so this is going to be the spirit of the talk, too. It's going to be confused, which I imagine fascinates you. So what's this business of tabletop quantum gravity? Well, it's quantum gravity is pretty much, not only, the idea that Einstein taught us that matter sources a space-time geometry, and so quantum matter should be sourcing a quantum geometry. And this idea is there without thinking about what's going on at the center of black holes, without thinking what's going on at the Big Bang, without thinking what's going on at high energies. And so the idea is, okay, let's forget about all that. Let's go to the earthly Newtonian regime and think what happens when we put quantum matter in superposition and try to detect that, which started all this business of maybe we can close the lights or something because I have these black slides. Yeah. Which started this business of let's put two masses in path superposition. They're gonna the Newtonian potential, if you want, is going to be in some sort of superposition. And I've been making the point that this is really a superposition of spacetimes. As striking as it sounds, when they do this experiment, we would be able to claim that we have set spacetime in a superposition in the laboratory. And this has been somehow remade in a series of papers, the two most recent ones here, and another one I'm going to talk about just in a moment. So, following up in this discussion, the next thing we wanted to look at, this was with OFEC, who has done a lot of work on this, was, and something that Markus Aspelmeyer talked just previously, is to instead of having discrete variables, so instead of putting paths in superposition, to have oscillator states. So these are continuous wave functions. However, you can think of the path degree of freedom being in a continuous superposition and analyze that situation with a path integral in a covariant formalism, make again the point that this is going to be now a continuum of spacetimes in superposition. And in addition, we were able to verify that these are radiation-free geometries, so whether you put accelerated trajectories or not, so I will come to this in a moment. You get the same result in the entanglement in a generalized protocol where you have two Gaussians in superposition. So this is pretty much both the idea of having the path degree of freedom and having the delocalization. And the main takeaways is that you get the same interpretation, spacetime in superposition, and you see clearly that the delocalization of the wave packet or the distance between two paths is really playing exactly the same role physically. Which we used very recently in an idea to detect tiny black holes, which could be what dark matter is. Let me say that an important point, which you should keep in mind, is that Feynman's idea that was cited also previously was to put a mass in superposition and see that a test particle would go in a superposition of trajectories. So this was about detecting the fact that the gravitational deflection would be in a superposition, which is not what is the idea in the modern discussion about mediated entanglement. It's very easy to put down the numbers that people talk about for doing these experiments, calculate what the deflection would be using Newton's law, force equals mass acceleration, and you see that the deflection would be in fact minuscule, 100 times less than an atom. What is going on, because you have entanglement, is that you are looking at the entangling phases, which do not see this deflection. Now, you can use this idea also for Josephson junctions, where you have a delocalization of the wave function across the junction, and say that if a Planck mass particle passes and you stack many, many, many of those, like a billion of them, you're going to get a tiny current because of the interaction of the electron mass with the mass that is passing. But if you put enough of them, then you could actually get a measurable signal. And this is something that goes back to a story I was doing in my PhD with many other people. There's many papers. You could see this recent paper, which is very technical about loop quantum gravity, but see the citations in it, predicting that, suggesting that maybe what dark matter is Planck mass black holes. which would have about a Planck length in size, and so would pass through everything, but they would still interact gravitationally as strong as a dust particle of Planck mass. So you could be able to detect these things. So this is one path in which thinking about mediated entanglement produces new ideas. This is about detecting dark matter. Another direction that is interesting is thinking about protocols that do not involve entanglement. There's a previous work by Richard Hall and others, including myself, of detecting non-Gaussianity production in Bose-Einstein condensates. We're working on something now which is about detecting quantum gravity corrections in thermodynamical observables, which is pretty promising, I must say. That's with Bose-Einstein condensates as well. And I think the direction that the field is going in this, let's say, subdirection is to think of superfluids, because naively you will get a very big magnification due to the significantly larger mass density. Bose-Einstein condensates are the simplest things to play around, mathematically speaking. But obviously one should think about superfluids, and there's a few ideas being discussed with Sugato Bose, with Richard Hall, and also with Brigitta Whaley. There's nothing really that has come out clean so far, but I suspect a few things are going to come out from various people with superfluids. Another completely different idea is to think of superposition of rotations, which is something we're doing with Andrea and Gerard Higgins, who is the main person pushing this, which is to take into account that rotational energy gravitates, to use this fact and create a superposition of masses, which is something that is also unique to gravity. You do not get superposition of charges in electromagnetism. And this also includes the speed of light in a substantial way. There is a genuine relativistic effect. It's pretty difficult as an experiment. How difficult? Well, let's see. We should have some sort of answer in a few months on this. So where is this going? I started doing my PhD with black holes, with hard, non-perturbative quantum gravity. Everything I've talked about pretty much you can think of as superpositions of Newtonian potentials plus the mass energy equivalence. Is there something more exciting to come? Well, I don't know. Maybe. I think we should be thinking about non-perturbative effects like time discreteness. Have a couple of very speculative papers on this, but I still think there might be something there. And also effects that are only specific to gravity, like superposition of mass, the fact that there is no dipole and no screening allowed. There is a cute idea out there by Igor Bykovsky and others about the photoelectric effect, the analog of the photoelectric effect of gravity in gravitational waves. We shouldn't lose hope that maybe there's going to be something more to see. It's going to be difficult, but the main point, and I think the reason many people here at IQOQI and around the world are interested, is because these ideas, because they're in a sense simple, also allow to clarify and revisit various conceptual issues, like what is a subsystem, what is locality, what are degrees of freedom, what are reference frames, and what are observables. So let me quickly say how you can go from this tabletop quantum gravity story to these issues. Sketch one path. So it starts from the effort to have a theory-independent line of argument for the non-classicality of the gravitational field, which is this idea that if you have two systems interacting only through a middle system, the mediator, and they become entangled, then the thing in the middle cannot be classical. Given that GR is a classical field theory, this would falsify GR in a theory-independent way. It would, hopefully. And the way people hope to make this work is similar to the Bell case, where essentially you have some property which is correlations, entanglement, which you want to check with the experiment, and then you want to push yourself into a dilemma where you're going to drop something that you really want, or both. And typically here you would drop, you would want to keep free choice, and you would drop local realism. So the idea for mediated entanglement is to force one to drop, to keep locality of interactions and drop classicality. Now the problem that you have when you see these theorems and how they work is that it's not clear what is meant by locality, which is why we went to this effort, which, I mean, this paper, which was a letter, clarifies this a lot, where we show that entangling phases are, first of all, actions. They are covariant actions of a local field theory if you're working with a local field theory, and so they're going to respect space-time locality. They do not build instantaneously. And so it's not really just the potential there, which is instantaneous, the Newtonian potential. However, still, this does not finish the story, because it's not really the locality that people are talking about. They are assuming something else, which is subsystem locality. And in this recent paper, which is mainly, the calculation is mainly due to Andrea, it took us a long time to figure this out. We could show that microcausality of quantum field theories allows you, under a certain set of approximations, which is more than suitable for this regime, to really write down the evolution in a subsystem local form, where you have boxes that never touch both matter systems. And this really allows you to have the definition of the mediator, in the sense that these no-go theorems want to do that. The idea is that you can split in many, many intervals where the sources are at space-like separation, and at each such interval you get the subsystem local decomposition, and at each such interval you get the boxes to commute as well. Where this is going is essentially putting QFT on a quantum circuit, and something we're working on now is to generalize this, bringing together algebraic quantum field theory and general probabilistic theories. Let me quickly say now how this goes into the degrees of freedom, and what are degrees of freedom. We try to do this with a silly argument. So imagine that you have a chain of spins, the orange things, quantum systems, which are interacting in some way that has a delay. All right? There is some finite time t so that each pair can interact. And you send some influence from the left, and it's going to go to the right. Quantum information is not going to pass through a link C here in the middle that is classical, because it doesn't fit in some sense. Now, let's send now the delay to 0, all right? So now I have action at a distance. I have an influence from the left, doing something on the right instantaneously. But it seems that still quantum information is not going to go through, right? While classical information will. So in this sense, why do we even make such a fuss about locality and assuming locality? It isn't really about locality. It is about whether you have something classical in the middle or not. But the thing is that locality is related with the question whether you have degrees of freedom to begin with, whether there is a mediating subsystem. And let me sketch this in a silly way, which is you take Poisson's equation, that's like Newton's law, in vacuum, and you see that there is a unique solution, right? So in this sense, we say that this potential doesn't have a state space, so it doesn't have degrees of freedom. And then you put the wave equation, so you add a second time derivative over Minkowski space, and then suddenly this thing has a whole life of its own. You can basically have any arbitrary function you want here, any sort of waveform that is propagating so long as it remains massless is going to satisfy this equation. So phi is now a thing, it's a field, right? So now you have degrees of freedom. And naively, think of it this way. This is your wave operator. If you send the speed of light to infinity, it's going to go back to the Poisson equation. So this limit is killing the life of phi. And all this gets very, very confused once you dig into it. I know that Andrea slightly disagrees with me because he thinks that this thing still has a life of its own, but maybe he'll talk about it in his own talk. So the debate is still evolving around this idea that whether there is a mediating system or not, what are the true degrees of freedom, and how gauge invariants complicate things. We know that nobody can really write these true degrees of freedom. They depend non-locally on matter, and so on. Which takes me now to how quantum reference frames could help in this story. In this paper, we have a small prototype example of a use of a quantum reference frame, which makes the point that if you do this quantum controlled diffeomorphism that also Časlav was talking about, on each branch, you can isolate the degree of freedom that is in a superposition, which is the distance in each branch, which is the invariant thing, the diffeomorphism invariant thing in each branch. And notice that this is a non-local degree of freedom. It's not at a point, all right? Another prototype example, which is what Časlav was talking about, this paper with Anne-Catherine and Victoria, is that you can define definite or indefinite causal order in this game of quantum controlled diffeomorphism, what is invariant under quantum reference frames, if you want. And this other prototype example is also a non-local thing, because proper time is, again, not defined at a point. You need 2 points. And you need a curve that connects them. So let me bring another thing in the game, which is that if you've been through a trajectory of quantum gravity, you know that there is a horrible problem in gravity which goes to the classical theory. It doesn't have anything to do with the quantum theory, which is a problem of observables, which is essentially that this group, diffeomorphism group, is just horrible. It's immense. Nobody knows how to define it. Well, you know how to define it, but you don't know how to, manipulate it. And there is this very cute paper that we wrote with a friend a few months ago. It's also a letter, which is very theoretical, is with this abstract field of mathematics called descriptive set theory. But it shows that somehow the reason that you cannot find these observables that are invariant under this huge group is because it's impossible. They are not definable mathematically, essentially. They are not definable in any algorithmic way or any analytic way that you could imagine. You have to use the axiom of choice to say they exist in some sort of theological manner, and that's it. So how do you put all this together? Well, first of all, I think we should de-obsess ourselves about trying to find observables that are local and think about global observables. The second is that we should think in the discrete, so bring graphs in the game. Think about coordinates as names instead, and changes of coordinates are renamings. This relates to a paper with Arrighi. And in which case things are going to be definable now, and explore quantum coordinates and reference frames in this setting, which would also be more amenable to a known theory, Lucan gravity, which has under control the notion of quantum space, and test these ideas. So this is pretty much the direction in which I'm going, and I see the things I'm doing to relate to each other. And I leave you with a quote from my PhD supervisor, and that's it.
Great, Marius, thank you. Do you have any questions?
So take the space of false solutions of Einstein's equations.
Okay.
Think of functions from that space of solutions.
S is the space of solutions of the Einstein equation.
Yes. R is some space in which they're going to take values, which can be very generic. It's called Polish space. Just imagine anything you can imagine. And ask if that R can be definable in any analytical way, while demanding that this observable is complete, meaning that if I give you two diffeomorphically inequivalent solutions, it can tell them apart. It's going to take different values in this R. And the answer is that you cannot have both. You cannot have them both complete and definable.
So this S then is the set of Einstein's. So it's basically any solution of Einstein's equations.
If you take all solutions, it's very easy to get it. The striking thing is that you get it in vacuum as well.
Okay.
Yeah.
So already in vacuum.
Already in vacuum. Yeah. I mean, I didn't say because I didn't want to go into it, but that's the main point, that you get it in vacuum.
Next time. I'd like to hear about your personal view on these. You mentioned very briefly, because it's something which is usually known, that you cannot make superposition of different charges, states with different charges. But usually we consider different mass superposition of masses in different positions, or
yeah, you can make
different masses like internal energies or something like that. And basically, they are the origin of these two conservation principles actually are very similar. So, why there's no like super selection rule associated to, for instance, masses and position of mass, center of masses, as we usually assume that there is for electromagnetism, and
I don't know why there isn't one, but.
Because it's usually, I don't see the difference actually. Apart from the fact that gravity is much weaker, then probably from the observational point of view, maybe it's more easy to obtain the superposition of masses without keep coherence of superposition of different masses. But it's not much different than, for instance, superposition of charges, right? So. Do you have a personal view why they actually seem to be so different? Why theoretically?
No, I wasn't making any strong statement. I was just saying that if you have a super.
No, I know. I just want to. Yes, I know. I just want, because since you have worked with this kind of things, I just wanted to see your.
I was speculating on what could be an interesting direction to go, and in relation, in particular, to this work of superposition of rotations,
right? Yeah.
Where you have rotational energy and you use mass energy equivalence to bring in really the speed of light. And that's something that is somehow, I cannot think of an electromagnetic analog. That's all I was saying. Yeah, the other questions I'm not sure I follow them. I don't have any deep reason why we don't, have superposition of charge in electromagnetism and in gravity. It should be possible, but we should also, we haven't seen that, but we suspect it's possible.
We've seen, I think isn't it fair to say that we have seen superposition of masses when we, for instance, have an atom in different energy levels, superposition of different energy levels? That's superposition of mass, right?
Well, no, you have to see it gravitating, right?
Yeah. No, I know, yeah. But we have the superposition of masses. We didn't measure the gravitational, but we believe that we can have that. But for charges, usually it's considered that it's impossible. And
that's right. That's right. Two things. One is different to believe and different to know. The other is I don't know why you don't. I don't have an answer to that. Why you do not have a super selection rule in gravity? I don't know.
So if there are no more questions, thanks again, Marius.
If you want, I give you a 5-minute warning when it's 15 minutes.
Perfect, yeah.
But yeah, don't
Thanks.
no need to stress.
Great, thank you.
This you can
this is the mic.
click on.
Galley.
Right, thank you. So today I want to talk about kind of two things at the same time. So on one hand, I want to talk about kind of principle-based approaches to physics versus model construction-based approaches, and especially in the context like interdisciplinary areas. And as a kind of case study, I'll use kind of debates around the nature of the gravitational field to illustrate these two approaches. Good. So, so principle versus model-based approaches, the example of quantum gravity. So there's, I guess, one of the main questions which have been occupying people for the past 6 years is how to quantize the gravitational field. So we have like string theory as an example, loop quantum gravity as another proposal. Okay, but then, I mean, why are people trying to quantize the gravitational field? Okay, let's take a step back. Okay, so say they want to unify quantum theory and general relativity. Okay, why do we want to unify quantum theory and general relativity? We want to describe quantum matter interacting gravitationally. And here I mean in the context where the quantum matter is back reacting on spacetime. Okay, so we know just like a quantum particle in a kind of classical field, right? How that works, gravitational field, like the Earth and the test particle that Časlav showed. But the case where there's back reaction, so the Earth in a superposition, this other scenario, these are the regimes why people kind of want to quantize the gravitational field. Okay, but does this actually require quantizing gravity? Oops, okay. Up. So, yeah, my claim is a priori, not necessarily. Right? I mean, there's not, it might be the case, you can just kind of think that we could have classical gravity and quantum matter, and that might be possible. So the first step people would do is if I kind of claim that, okay, maybe it's possible to have classical gravity and quantum matter, is to construct a model. So this is the model-based approach. So I take general relativity, okay, and then, for instance, instead of T mu nu, I now have an expectation value, okay, so T mu nu hat is a quantum operator, it's expectation value on a state, and I have this so-called semi-classical Einstein's equation. So this is a model of classical gravity interacting with quantum matter. So you do this, then you work some stuff out, and you find that the kind of matter degrees of freedom follow what's called the Schrödinger-Newton equation. Okay? It's a nonlinear Schrödinger equation. Okay, so we have this nonlinear Schrödinger equation, so then you've built your model, and then you go, oh, wait a minute. You see stuff like violation of the uncertainty principle, and then if you try and talk about multiple systems, you see the appearance of signaling, okay? Faster than light signaling, typically. So, in this model-based approach, essentially, I haven't shown that you can't couple classical gravity and quantum matter. I've just said that one, actually quite natural model leads to inconsistencies. Okay, but this does not entail that all classical quantum models are inconsistent. Good. But okay, so let's think. So now let's take a kind of like foundations, put our foundations hat on, and like what's the type of methodology that we like. Okay, so we'll just use Bell's theorem as a kind of canonical result. So what Bell is doing is, okay, sure, he was thinking about Bohmian mechanics, okay, a particular model, classical model of quantum mechanics. He noticed it had weird properties. Okay, but in Bell's theorem, he actually kind of looks at all possible classical models. Any classical model of quantum theory must be non-local. Okay, and this is what I'm calling a principle-based approach. Okay, he's not looking at a specific model, but he's kind of talking about the principles which generic models must obey. Okay, so this is what I suggest. It's principle-based approach is what I suggest could be useful in this context also. So instead of constructing specific models of classical quantum couplings, maybe finding they don't work, let's just characterize all consistent classical quantum interactions. What features must they have to be consistent? And that might then help guide us. Okay, and first, I'm just going to give you a very simple example. So it is possible to couple quantum and classical systems together in a consistent manner. It's quite useful, it is, because it's called measuring things. Okay, so I have, in this example, a quantum spin half particle and a classical measuring device, which is a two-level classical system, right? So diagonal, I'm representing it by a diagonal density matrix. Probability 0 of the measurement device being in 0, and probability 1 of being in 1. Okay, no coherence term, it's just diagonal, and my quantum state can have coherences, okay, so generic. And the interaction is, I start in a product state, so my system is in state psi, my measuring device in state 0, and the evolution, with probability alpha squared, they're both in 0, and probability beta squared, they're both in 1. This is like the kind of decohered version of the von Neumann measurement scheme, if you want, okay? Okay, so, okay, good. It is actually possible to couple quantum things and classical things consistently. Let's look just for intuition to a few features. Oops, okay, a slight lag. So this interaction here is irreversible, okay, or stochastic, probabilistic, and it features back reaction, so information flow from the quantum to the classical. So if I look at the density matrix of the classical system after the interaction, right, it's this mixed state, it depends on the initial quantum state, which is very good. It tells us that when I measure something, I learn information about the quantum system. And just to be clear why here we kind of have consistency, it's a representation which is linear in probabilities. We have like CP-TP maps and all this kind of machinery of operational quantum mechanics. When you have like CP-TP maps or like stochastic maps for classical systems, you'll never have like violations of like the Heisenberg uncertainty principle or signaling, right? You kind of enforce consistency. So that's, I think, one of the benefits of this operational approach. Okay, so now I've shown that it's, if we're trying to characterize all possible classical quantum couplings, there are at least some consistent ones that we're talking about. That's a good thing. Good. So, okay, so here I'm going to talk about the general case, which is based on this paper. It's joint work with Flaminio Giacomini and John Selby. Okay, so what's the general setup? We have a system S, which is quantum, a system G, which is classical, and they interact, right? That's just the basic thing. So S goes in, G goes in, then have some output states. And we're going to characterize all consistent classical quantum interactions. Okay, note in the paper we do this for like GPTs, so non-classical systems more generally, but for the purpose of this talk, we're looking at quantum systems. Okay, so I've already introduced the notion of like reversible interactions. So I is reversible if there exists another interaction inverse, which is just the identity. So unitary quantum mechanics, if I FL psi by U, oops, I can undo it. Well, okay, that's skip. But unitaries, you can undo them. The next important concept with this information flow or back reaction, right? So if I have two systems, 1 and 2, which interact, okay, we say that information flow from 1 to 2 if the state of system 2 after the interaction depends non-trivially on the state of the first system, right? So in gravity, that's kind of back reaction, right, in a sense. That's what people call it. You can phrase this just in terms of probabilities. There's like signaling from 1 to 2, if you like, the kind of device-independent way of thinking. Okay, I'm going to give a kind of, the proof is actually very simple, so I'm going to give an intuition. I assume S is quantum, G is classical, the interaction is reversible, and there's this back reaction. So first step, I just apply my interaction. So I have two new states where, because of this back reaction, I've extracted some information about system S, right? System G, there's some imprint of the information about S. So i.e., there's a measurement of S, right? I've carried some measurement. So here, this classical information about S, I kind of copy it. I keep a separate copy in another register. Next step I do, it's reversible, so I can undo everything that just happened, right? So I return the two systems to the initial states. So what I've constructed here is a non-disturbing measurement, because the state of the system is returned to its initial state, with information gain, right? Because here, because of this signaling, I got information. there's theorems which tell us that this is impossible. If you extract information about a system, you must disturb it. Not just quantumly, but in general probabilistic theories. That's essentially all the proof is, right? So, to make it look better, you put in a theorem, and you say the following. Okay, so here, essentially, okay, maybe the structure of the theorem is a no-go theorem, because I took a bunch of assumptions and showed they can't hold together. Therefore, at least one must be violated, okay? So assumption one is the system S is fully non-classical. I'll explain what fully means in one slide. The interaction is reversible, is the second. 3 was this information flow or back reaction, and 4 was G is classical. Okay, so as a quick aside, there is kind of one fully non-classical is I'm assuming that the system S is not superselected. Okay, so when you have superselected systems in quantum theories, these are block diagonal matrices, you can extract information reversibly, right? Because you can measure which sector, am I in the top left or bottom right, without disturbing the system, because it's kind of classical information. So that's the small technicality, which I won't bother with now. Okay, so then, now this is what I'm talking about, the principled approach. In any kind of coupling, where I have a classical system and a quantum system, okay, so if I assume G is classical, well then, either I could reject the first premise. So sorry, if I just assume the gravitational field is classical, I could reject the first premise, that the system is quantum, right? I mean, so classical GR and classical systems is fine, that's good, and it's reversible. Otherwise, if I want to hold on to my system being quantum, I could reject reversibility, okay? And number 3, this back reaction is rejecting the influence of matter on gravity, which, yeah, we kind of want to keep, really. So it seems that reversibility is the only kind of thing which we might want to change. Good, so to return to the question of should we quantize gravity, I'm saying that essentially your commitment to reversibility, if you're committed to reversibility, you say physics is fundamentally reversible, quantum field theory is reversible, general relativity is reversible, successive theory must be reversible, then yeah, you have to quantize gravity. Okay, or classicalize matter, which is actually what I said when in this semi-classical approximations you violate the uncertainty principle, is because your quantum matter has inherited classical properties, essentially. Right, so when you have reversible couplings between classical and quantum, essentially it kind of the classicalness can spread to the quantum, or the quantumness can spread to the classical. Anyway, so so historically, okay, so this is now going back to the kind of idea of model building versus principle. It's why are people historically in favor of quantizing gravity? Is because there have been a number. They didn't just like decide this, right? They had lots of debates and arguments, thought experiments, kind of no-go results. So like Feynman and Aharonov have all these types of results. But actually, when you look into a bit more deeply, they all assume quite implicitly, often, reversibility, very implicitly. Okay. So I'm saying that that's why sometimes it's good to actually have like kind of clear statements and theorems, no-go theorems that make the assumptions clear, especially in interdisciplinary areas. Okay. So, building models and dividing thought experiments is useful for guidance, but principle-based approaches allow for greater precision and clarity. Okay, so the theorem shows that any classical model must be irreversible. It doesn't show that such a model exists, right? Because when I'm talking about classical quantum couplings in the context of GR, you'd want something like diffeomorphism invariance, at least spatially, for instance, and other properties like this. Okay, so it turns out there is such a model, right? So Jonathan Oppenheim, who gave a talk here, his post-quantum theory of classical gravity, he couples the space-time metric in a spatially diffeomorphic way to quantum field theory in this consistent way, exactly because, so the quantum fields back react on the space-time metric, but in a stochastic way, essentially. Okay, good. So just to go back, kind of the kind of like collective wisdom, right, over the past 60 years. I like it. Milnik has this very nice paper, and he says, at the end, so he studies these couplings in the context of reversibility, and says, though it may be very difficult to quantize gravitation, it's even more difficult not to do it. Okay, which if you have reversibility is true. Okay, so I just want to stress this, right? And so then when you notice this, it offers another way out, which is irreversibility. Okay, I just said this already about this kind of like important to have this interplay between them, especially in these interdisciplinary areas where people don't necessarily share common assumptions. Okay, and just to kind of finish, so what next? In all my discussion about what physics is about, models and principles, we missed the kind of crucial ingredient, which is experiments. Okay, so we've had some talks about this, and yeah, I really think that these gravity-mediated entanglement experiments will actually allow us to adjudicate between, for instance, the kind of model suggested by Jonathan Oppenheim and kind of other approaches which do choose to quantize gravity. I like a lot that Marius said, actually, I mean, modulo background assumptions, right? Like, there's still lots of theoretical work that's being done that needs to be done on these experiments. Yeah, and that was my talk, so thank you. Thank you.
Any questions? Actually, I have a question.
Yeah.
So I actually have two questions. I'll ask you first one and then the other one. So about Jonathan's model, I've heard rumors that it's not clear whether it predicts entanglement or not.
Okay.
And there's a follow-up question to that.
Yeah.
Is there any work in making it into a GPT to apply your theorem?
So to the first question, I haven't worked out the details. I know that in his first paper, he does say that these GME experiments would kind of essentially falsify the model. But so I haven't worked out the details. That's possible. I mean, that's definitely possible. So actually, his approach is in a sense already in this GPT setting, in that he uses a kind of convex framework of quantum mechanics, so like density operators and CPTP maps. So in this sense, it already works within this framework. Yeah.
So shouldn't you be able to apply in the system? Like you see that it's quantum, you see that the other thing is classical, therefore it's
Yeah, exactly. Yeah. It's well, I guess what's interesting about his approach is more that he provides specific couplings, and it's exactly in this kind of general relativistic like scenario. So he can say quite a bit more just than because exactly. So our theorem says we look at his thing and says, oh, it had to be irreversible anyway. Right. But then what's interesting is he can talk about like quantum fields and curved space-time and like things like this. I'd say. Cool. Yeah. Thanks.
About this particular, I don't know if you remember, but in this particular construction that you mentioned, is there the analogous or the equivalent for the semi-classical Einstein equation would be something like what? Do you remember? How the quantum matter actually distorts the space? It's still a metric theory for gravity, or it's a completely different theory for gravity?
In the semi-classical one, or in the
in the one that you mentioned?
Jonathan Oppenheim? Yeah, so in it, you have, so you have the classical degree of freedom is the kind of space-time metric. Okay. That's the kind of phase space. And then you have these classical quantum states, and then you have kind of quantum fields at each like phase space point, in a sense.
So the Einstein's equation is substituted not by the semi-classical.
No.
Just the expectation value.
Yeah, it's exactly. It's definitely not. Essentially, it becomes a master equation, and then in a certain limit, you recover the Einstein equation. So there's a limit h bar goes to 0, so where your matter becomes classical, you recover more or less the Einstein's equation. So it's Einstein's equation, then you add terms for diffusion, decoherence, this type of thing. So it's very much a kind of open quantum system description. Yeah.
Any other questions? All right, so we're actually running ahead of schedule, so we're taking a break.
We're going to be continuing on time at 5:30. There's a lot of drinks and some food left from the coffee break, so feel free to grab everything you want, and we're going to be opening windows so that we're fresh for the last 3 talks.
Yeah.